currently? Because I see. Okay, Chen, are you still sharing?
Hello. No, it's not my. I'm not sharing at the moment. I don't know who is sharing.
Okay, I think we can get started. So welcome everyone to the first session of the top quark and electroweak physics session. Today we will focus on precision physics with W and Z bosons during the first part of the meeting, during this sub-session. And then later on, after the coffee break, focus on top quark single and double differential cross-section measurements, and finally concluding in the third session with further discussion on precision measurements. Just a reminder, we also have a dedicated top quark discussion session later today, which is on the agenda. You can find it on the agenda. We already have something like 42 participants connected to this meeting, and the list is growing. I just wanted to say a couple of reminders to the speakers. You have about 18 minutes plus 7 minutes of discussion, question and answer session. I will interrupt you briefly 5 minutes before the 18 minutes is up to just let you know that you have 5 minutes remaining for your talk. For the attendees and participants, if you have a question, you should raise your hand and then we will unmute you. You can ask your question. Please state your name first before asking the question. In case if it happens that you cannot ask the question directly, you can put it on Zoom chat here. We can transmit the question. There's also the Mattermost channel you can use to post the questions. We will try to monitor that as well. Okay, that's all I had. Our first speaker is Chen Wang, who will tell us about the recent measurements of electroweak boson properties at D0. So Chen, please go ahead and share your slides.
Hello, can you guys hear me? Yes, I have, let me share my slides.
Yeah, we can hear you and we can see your slides.
Yeah, okay. Hello everyone, I'm glad to be here on behalf of the D0 collaboration to represent our recent study of the normalized WPT distribution in the ppbar lesions data. Please go to slide 2. First, I want to talk about the motivation of the study. The vector boson PT is described by the QCD calculation, and from the leading order, for example, the Feynman diagram that showed the left, the vector boson PT is equals to 0. And if we including higher order effect, for example, we including diagrams like next to leading order, like the right, and the vector boson PT will arise from the initial state pattern emissions, like the gluon shown in this diagram. So this kind of studies about the vector boson PT distribution as a test of the QCD predictions. However, in the ppbar lesions, the production here in our data is dominated by the valence quark. However, in the LHC experiments, it involves the C quarks. This is the major difference from our data and the most of the data in LHC. And for the low vector boson PT region, this is what our study focus on. This is the the production is dominated by the multi-soft gluon emissions, and the QCD predictions from a soft gluon resummation formalism we usually call CSS is you have a very good prediction on this region. And in this formalism, it uses the form factor with the 3 non-producible parameters G1, G2, and G3. Usually we call this BL1Y or other forms to have to be have to be input, and these 3 parameters it's for our study is fixed to the previous measurements. And so such kind of study about the vector boson PT distribution can be used to constrain models of these non-projective approaches. And it could also benefit other related electroweak parameters measurements, such as the WMS measurements, which is has a model uncertainty related to this distribution. Please go to slide 3. And for slide 3, here is a brief introduction of our study. First, this is the first Tevatron Run 2 WPT study, and it's also the first study at 1.96 TeV. And it's based on the latest D0 published WMS measurement, and we use the same data sample. We share the same background estimation strategy. We use the same detector calibration methodology and the same parameterized Monte Carlo simulation, which we call PMCS. And in this study, we focus on the low WPT region, which is the W boson PT smaller than 15 GeV. And here, this is sensitive to the QC non-predictive parameters. And we provide reconstruction level results and additional faster folding procedure and for the comparison to other models. And please go to slide 4. And here, this is a brief introduction of our D0 detector, mainly from 3 parts. First is the central tracking system, then is the calorimeter, and then the most outside is the muon system. For our central tracking system, is made of 2 parts: the SMT and CFT. It's have a 1.9 TeV solenoid magnet, and for the calorimeter, it's a liquid argon plus uranium for a very large range of coverage until eta equals to 4.2. And for our electron, this is used for the electron energy measurement and for our hadronic recoil reconstruction. And please go to slide 5. Here for slide 5, our sample is under selections. Our sample is the part of the Run 2 data for 4.35 inverse ttbar at around 2 TeV, and the trigger requirements is at least 1 electromagnetic clusters in our calorimeters, and the transverse energy threshold is from changing from 25 to 27. This is depending on the instant luminosity. And then for the offline selection, we require our electron candidate have a large PT larger than 25 GeV within the 1.05, the center of our calorimeter, and pass shower shape and isolation requirements. And for the W candidate, we require at least 1 electron candidate and have a transverse mass from 50 to 200 GeV and have a missing ET or missing PT for larger than 25 GeV, and the hadronic recoil UT is smaller than 15 GeV. Here, I want to emphasize that our hadronic recoil UT vector directly represents the WPT. It's the vector sum of the reconstructed energy clusters in the calorimeters excluding deposits. So the missing ET could be directly calculated from this by the hadronic recoil and the lepton PT. And this missing ET here just directly represent the PT of the neutrino, and for the transverse mass is defined in the equation here. And please go to slide 6. And for slide 6, I want to talk about our detector calibration. And first, for the electron energy is calibrated using the same mass distribution, and we have 2 parameters for the calibration, the alpha and beta, and we have a quite good energy to reduce the energy dependent effects of energy dependent bias of the lepton energy. And for the hadronic recoil, this is also calibrated using Z candidates. And here for the Z candidates, we can define eta imbalance. Eta here is the direction bisected to 2 electrons, and we define this eta imbalance as the imbalance between the UT and the transverse PT transverse momentum of the dilepton pair on this eta direction. And in the W candidates, and because there is only one charge dilepton reconstructed, so we use different the recoil components in 2 different directions, the parallel and the perpendicular components to the electron direction, using these 2 components to test the modeling of the hadronic recoil. And the distribution of the parallel and the perpendicular components of the hadronic recoil is shown in the 2 figures below. As you can see, generally, it's quite a good agreement between the data and the prediction on our hadronic recoil response. And please go to slide 7. Here for slide 7, this is our background estimation. Generally, our background estimated with very good precision, and generally we consider 3 kinds of background. First is W tau nu, and with this tau lepton decayed into electron, has an electron decay. And for the Z2E, these kind of Drillian events, and for the finally for the multi-jet backgrounds. And for the tau background, this is also estimated from our Monte Carlo simulation. This is our faster Monte Carlo simulation, also with the same generator as our default PMCS. And for the ZE and multi-jet, for the ZE background, 1 electron is escaped our detection. And for the multi-jet background, 1 jet is misidentified as 1 electron. So these kind of things is directly estimated from our data. And for the so for these 3 kind of background, generally the main for W is around 1.6% W tau background, and Z and the multi-jet are all around 1%. So totally the background is less than 4%, and the uncertainty due to background estimation is generally negligible. And generally it's a good and as you can see in the red plot, this is hadronic recoil distribution that we have after our background estimation. Generally, you can see it's a good agreement between data and prediction at the reconstruction level. And the table in the bottom is the fraction of events in the UT bins. And in these 5 bins we used for final observation, and the total uncertainty, this is the combination of the uncertainty from the background estimation and the statistical uncertainty from the data. And please go to slide 8. And for slide 8, here we want to talk about PMCS reweighting, which is used to compare the different theory predictions to our reconstructed level data. Here in our PMCS framework, we just directly reweighted the WPT and W rapidity to the distribution, and this is related to other theory predictions. And the default PMCS is a response generated by response, and with a BL1Y non-perturbative parameter non-perturbative function, and the result. And for the 2 approaches, generally we consider the theory predictions from 2 approaches. One is from the resummation calculation, and this is from the response, and this is focused on the non-perturbative functional form, like BL1Y or the transverse momentum dependent BL1Y. And for the pattern shower, and another thing is a pattern shower approach from the PCR. We use the PCR8, and this is focusing on the different PCR8 tunes from other collaborations. And the systematic uncertainty here is estimated by changing the parameters in our PMCS framework. And this is separately estimated with each model, and is dominated by the uncertainty due to the hadronic recoil calibration, and the bin-by-bin correlation is also estimated with our PMCS simulation. And the fraction of events of the background subtracted data compared to different predictions is shown in these 3 figures at the bottom. And as you can see, the first 2 is related to PCR8, and the last one is compared to the response. And please go to slide 8. And for slide 8, finally, we do a chi-square calculation, and the chi-square value between the data and the related PMCS are calculated, and all these 5 UT bins are considered. And however, the number degree of freedom should be 4 due to the normalization, because we always normalize our Monte Carlo to the data, and the bin-by-bin correlations are taken into account. And the uncertainties due to the resummation calculation of the response generator, and the uncertainty due to the tunes used in PCR, this is ignored. And the PDF, however, for the PDF uncertainty, this is negligible on the transverse momentum of the W boson, since the transverse momentum is related to the QCD scale of the quarks. And for the conclusion that here showed in the table below, here we show the chi-square over the number degree of freedom and the corresponding p-value and the significance. And here 2 models are excluded. First is the PCR8 with ATAS minimum bias A2 tune with the CTEX 6L1 PDF, and the other is the PCR8 with the CMS tune, also with this CTEX 6L1 PDF. And other, as you can see, other PDF tunes except the default ones, and are all disfavored, has a significance larger than 3. And our default theory prediction response plus the BLNY, and the default PCR8 plus the CT14 HERO2 NLO PDF has a very good agreement with our data. And for the response with the transverse momentum dependent BLNY, and this has a not very good agreement, is have a significance over 2. And please go to slide 10. Here for slide 10, I want to talk about the comparison to, if we want to compare our data to other theory predictions, not included here. And generally, we can do these things for 2 approaches. And to achieve this, first, we can provide an unfolded level, particle level results. And this can be used directly compared to the theory prediction. And the second approach, alternative thing, is that we provide a folding procedure that everybody can transform their theory prediction to the reconstruction level and directly compare to our reconstructed data. And these things, we choose the second approach, because when the statistical uncertainty dominates, and it can be proved that the chi-square value on the reconstruction level is equals to that to the unfolded particle level. So we will have the same precision of the comparison between the particle level and the reconstruction level comparison. However, when the systematic uncertainty dominates, and the systematic generally sometimes is related to the response matrix when you use in the unfolding procedure, and these kind of uncertainty will have a linear extrapolation to the reconstruction level, and we will have a nonlinear extrapolation to the particle level. This is why the precision on the particle level will be reduced. And another reason is that you have sometimes you use some kind of regularization procedure in your unfolding. You will require some kind of additional uncertainty on the particle level. Sometimes it's from the Monte Carlo modeling, sometimes it's from your regularization choice. And so this is why the precision on the particle level comparison will be reduced. And this kind of reduction of the precision would be greater when the resolution of the distribution is worse, and it will be smaller when the bin wise is enlarged. So this is why, either way, it will be a reduction of the precision. So this is why we choose to provide in our paper a folding procedure to have a better precision than the unfolded results. And please go to slide 11.
And
here's slide 11.
You have 3 more minutes remaining. Thanks.
Yeah. For the folding procedure, that here the folded number of events in the UTBNI could be calculated with the equation here. And here I want to show you the response matrix we have. This is the second reason that we don't want to represent to do the unfolding procedure. Here, the response matrix Rij is the probability for the events in one WPT bin and to be reconstructed into different UT bins. And as you can see in this response matrix, the maximum purity is something around 45%, is quite low. So if we directly do the unfolding, we will have for example, if we do the unfolding with the Bayesian method, we will have a large uncertainty due to the Monte Carlo modeling, which is defined as sometimes arbitrary and the correlations will be hard to estimate. So the instruction to calculate the covariance matrix and the detail of the whole folding procedure are introduced in the appendix of the paper, and our paper is now on arXiv. And the link here is the link to our paper from the Fermilab web page. And please go to the last page. Here is our summary. This time this is the first Tevatron Run 2 WPT measurement at around 2 TeV, focused on the low WPT region, and the background subtracted data compared to different predictions after PMCM simulation on the reconstructed level. And for the uncertainty is dominated by the hadronic recoil calibration, and the model uncertainty just ignored, and the PDF uncertainty here is negligible, and two models are excluded. And finally, a folding procedure is provided to compare with other models, which is not discussed in this paper, and to have a better precision than the unfolded results. And the model dependence of this folding procedure is tested to be negligible, and the chi-square difference is smaller from this folding procedure is smaller than the impact from the data fluctuation. And here is a link to our paper. Oh, thank you.
Great. Thank you very much, Chen, for this for presentation of these nice results and for staying on time. All right, we open the floor to questions and comments. Please raise your hands on Zoom, and we'll unmute you to ask the questions. Okay. While we are waiting, maybe I can ask one question on slide 8. When you were showing the comparison to different tunes and also to resbos, as you said, these are detector level distributions. So for resbos, you are basically reweighting your default Monte Carlo to the resbos distribution, or, because resbos is not a Monte Carlo, it's a generator, correct?
Yeah, it's a generator. And we use for this PMCS is parameterized simulation, so it can do simulation with any kind of generator you want. Just directly provide the inputs of the W events or the Z or the Julian Z events, Z to lepton events, and you will have and you will have the simulated events on the reconstruction level. So yeah, it's the response is our generator, so we can do any kind of simulation with any kind of generators with this PMCS. Yes.
Okay, and just to clarify, I think you said this, that the non-perturbative parameters here, they are not tuned to this data. You are taking them from previous measurements.
Now, here for the form factors, these non-perturbative parameters G1, G2, and G3, this usually is tuned with Z. It can be tuned with the Victor boson PT distributions. So we can tune with Z boson PT or W boson PT. And generally, due to the situation for the WPT is measured from the hadronic recoil, and ZPT can be reconstructed by the dilepton pairs. So generally, Z boson PT have a better precision. So the G1, G2, and G3 is already fitted with the Z boson PT of the Tevatron Run 1 data with a very good precision. Of course, if you use a larger data set, you can have a better precision, but we don't have that kind of measurement at the moment. So we still stick to the run one measure the G1, G2, and G3 from the Z boson PT. Why?
Okay, thank you. G, please go ahead.
Yeah, hello. As an XD0 member, I have a curious question. So this is the first PTW measurement. Does this imply that you plan to update it or focus on higher PTs?
Honestly, we don't have such kind of intention to focus on higher PTs, and I think for other D0 members who are focusing on these measurements, and we know that we no longer have the data. This is very this is a pity that we don't have the data for over 15 GeV.
Okay, thank you. I see.
Yeah.
All right. Any last questions to Chen?
One more comment. That we don't have the data, and we don't even have the tunes for that high data set. Because the higher energy, the more deposit energy you deposit into the calorimeter, so the hadronic recoil will be more difficult. So and you have less events to tune the hadronic recoils. So it's hard to go higher than 15 GeV.
Okay, and then just one last comment. You did. I was going to ask you why not also provide the unfolded results. I mean, I agree with you that it is more precise to show it at the detector level, and I think you showed in your last slide before the summary that you also provide the, let's say, the migration matrix to take into account the detector effects. So I am assuming this will be available somewhere, either in HEP data or in your paper, so that when people want to compare to your measurements with different predictions, they can directly obtain these numbers.
It's at the moment all the systematic, all the response matrix for the nominal value and the response matrix for all the systematic variations are all provided in this paper, and we have a plan to put it on the HEP data.
Okay, very good. G, go ahead.
Yeah, this is a good question, actually. So I was wondering whether you have a systematics on your folding matrix coming from different sources or models.
Why we systematic uncertainty, and we provided 11 systematic variations, and all the matrix for all the response matrix from these 11 systematic variations are all provided, so the readers can estimate the uncertainty, but on their own, because the systematic uncertainty should be model dependent. So this is why, if you have a different model, you should estimate your own systematic variations, and the same for the covariance matrix. And here these 11 systematic variations are 10 for the hadronic recoil and 1 for the electron energy, and so it is dominated by the uncertainty due to the hadronic recoil, as you can see in this is slide 20 here.
Yes, thank you.
Okay, thank you very much, Chen. I think we can move on. Thanks again for the presentation and the discussion. I think you can stop sharing now, and the next speaker is Riccardo Salvatico from University of Turin. He will tell us about W boson measurements with the CMS detector.
Hello, can you hear me?
Yes, Riccardo, we can hear you. One request, if it's possible, if you can also share your video to
yes, 1 second. Where is it? Sorry. Okay, can you also see me?
Yes, very good. Go ahead.
Okay, thank you. So yes, I will present to you some W boson measurements with the CMS experiment. The analyses I have selected for this talk are, first of all, the measurement of W boson rapidity, helicity, and differential cross-sections. Then the very recent search for the rare decay of a W boson into a charged pion and a photon, and the recently published evidence for WW production from double parton scattering. The first item I want to talk about is actually a remarkable set of measurements performed in the same analysis. That is W boson rapidity, measured differentially in the 3 helicity states of the W, differential and double differential W boson cross-sections, also in the unpolarized version, charge asymmetry, and a test on the constraining power of the PDFs. So the physical motivations behind these measurements are quite strong. First of all, measuring the polarization of the W boson is fundamental in determining its production mechanism. And then the measurements of the W boson rapidity, helicity, and charge asymmetry provide constraints on the PDFs. And we know that the uncertainties arising from imperfect knowledge of the PDFs strongly contribute to the overall uncertainties on the W mass measurements. This analysis exploits around 36 inverse femtobarn integrated luminosity, and the Ws are reconstructed in their leptonic decay. This gives rise to a rather large data set, as you can see. So we know that at the LHC, the W bosons are produced in a mixture of left, right-handed, and longitudinal polarization states, and that the rapidity and the helicity distributions are fully determined by the PDFs. But this means that if we are able to measure these quantities, then this results in a constraint to the PDFs and to their uncertainties. The physical principle behind this is that the W rapidity and the helicity affect the lepton PT and theta through spin correlations. And so somehow the lepton kinematics carry information on the PDFs. The W boson production cross-section with the subsequent decay into leptons can be written as a function of the W helicity fractions this way. The left term is the dominant at the LHC, while F0, the longitudinal component, is the least contributing one. And these Fi coefficients are strongly dependent on the W kinematics. And we said that the W kinematic properties are reflected into the lepton kinematics. So the 3 different helicity states of the W can actually be mapped in 2D plane, where the 2 dimensions are the PT and the eta of the lepton. Here you can see one of the simulated templates where the different colors correspond to different helicity states and rapidity ranges of the W plus. Then the strategy is to fit the data with the simulated PT eta templates to measure the rapidity, and not only for each W helicity and charge. Here I have presented a distribution of the observed lepton PT and theta unrolled into 1 dimension. So basically every bean in this distribution corresponds to both a bean of PT and a bean of eta. And the fit is performed in these 4 independent channels, and the different channels are combined by simultaneously minimizing the likelihood across them. The full set of systematic uncertainties is profiled in the likelihood. So it is essential here to control the systematics in the very fine granularity of the templates. The fitting tool which is used to sustain this very complex fitting apparatus is TensorFlow. I will show you now a few of the very nice results obtained. First of all, the rapidity dependent cross sections here in the plot on the left. For the W, they are separated for the W plus and minus, and for the left and right helicity states of the W, and they are normalized to the total fitted cross section. Here you cannot see the longitudinal component because it is actually not a freely floating parameter of the fit. It is fixed to the AMC at NLO prediction with a large uncertainty. On the right plot, you can see a measurement of the charge asymmetry, and by charge asymmetry I mean this parameter that I put here in the green box. And I remind to you that the measurement of the charge asymmetry is a very effective way to put constraints, direct constraints on the PDFs. And this is the first time that it has been measured at the same time, unfolded in rapidity beams and separated in the two W helicity states. The same measurements are also shown unpolarized, so basically summing over the helicity states. And then various double differential cross-sections are measured, differential in PT and theta of the leptons. In the top plot, you can see the normalized double differential cross-section, again unrolled into a 1D histogram. And here the lepton flavors are combined. In the lower plot, you can see the absolute double differential cross-section for the W minus, and for the two lepton channels separately. So these are fitted separately, and actually we can see that there's a good experimental agreement between the lepton flavors. Then by integrating the double differential cross-sections in one of the two dimensions as a function of the other variable, we can obtain the single differential cross-sections in PT and theta of the leptons. And with respect to a standard, let's say, single differential measurement, this approach has the advantage to be independent of the modeling of the lepton kinematics in the variable which is integrated away. The relevant uncertainties for this analysis are, first of all, of systematic nature. Uncertainty on the lepton momentum scale, on the lepton efficiency measurement, on the background estimation, mainly for the QCD multi-jet, which is the background with the largest contribution. And then on the theoretical and modeling side, the uncertainties on the PDFs and alpha strong are generally dominating. And on the statistical side, the uncertainty related to the size of the Monte Carlo samples is also relevant. Of course, the relative contribution of these systematics depends on the specific measurement, varies on the specific quantities which is measured. So, for example, the uncertainty on the integrated luminosity, which is one of the dominant in the measurement of the absolute cross sections, almost cancels out in the measurement of the normalized cross sections, as you can see from this plot. Finally, if we fix the cross sections in the likelihood to their expectation in all the helicity and the charge processes, we get the statistical power to constrain the PDF uncertainties. So here you can see the pools and the post-fit constraints of 60-hh representation of the NN PDF 3.0 PDF set plus alpha strong. And the mean constraint that is obtainable here is around 90% of the prefit uncertainties. Now we change topic. We are going to talk about the search for the rare decay of W2 pion and the photon. The motivations behind this search are numerous. First of all, the fact that no exclusive hadronic decay of the W boson has ever been observed. Some 95% confidence level upper limits have been measured, for example, on W2 pi gamma itself by the CDF collaboration and on W2 Disa base gamma, and also on W2 3-charged pions by the CMS collaboration. This is another very interesting result I invite you to take a look at. And these results can be compared with many more results on similar results on the Z boson. The theoretical predictions for these decays, if they exist, have rather large uncertainties. For example, the branching ratio of W2 pi gamma sets in the range 10 to the minus 9, 10 to the minus 6. So these kind of searches could also, let's say, provide a further motivation for the theoretical community to perform these calculations if possible. In this sense, the observation of W2 pi gamma would provide a good probe of the standard model and could provide also some insights on some QCD aspects, and the opportunity to measure the W mass through visible decay products only, which is, I think, an interesting scenario at future hadron colliders. Since at CMS it would be hard to perform this search inclusively, let's say by triggering on the photon, because of single photon trigger thresholds, which are pretty high to be sensitive to this decay, the idea is to isolate ttbar events. And this gives the chance to trigger on the lepton coming from the charged lepton coming from the leptonic decay of one of the two Ws. Then the presence of two V+jets is a specific trait of the ttbar topology, so it can also be handled to reduce the contribution from non-ttbar backgrounds. And finally, the rare decay topology is characterized by an isolated high ET photon and an isolated high PT pion. The idea then is to reconstruct the pi gamma invariant mass distribution and to fit it in order to measure the branching ratio. Another important item of this analysis is the pion isolation. So the pion from the decay of W2 pi gamma originates from an electroweak process. So the hadronic activity in its vicinity is expected to be low. Therefore, a pion isolation is calculated as the sum of the PT of all the particles contained in a cone around the pion, excluding the contribution from pi lab. And in this plot, you can see the pion relative isolation, that is the pion isolation divided by the PT of the pion itself. And it is quite evident how this variable provides quite outstanding discriminating power between the signal, which is the dashed red line, and the background. The trigger used is a single muon or a single electron trigger. And then at reconstruction level, the presence of only one isolated muon or electron is required in order to retain the event. The pion must carry opposite charge sign with respect to the lepton, and the photon must be also isolated. After that, the selection proceeds through BDT, which is trained on the Monte Carlo simulation and exploits the fact that the PT of the particles involved in the search is relatively high. The events contain a moderate amount of missing transverse energy. The number of V+jets, V-tagged jets for the signal is supposed to be 2, and the pion is supposed to be isolated according to the variable that I just showed. Then two BDTs are actually trained, one for every lepton channel, since the request of having a muon or an electron can basically bring two different background compositions in the two channels. And two control regions and two signal regions are defined upon these BDT outputs. Then the pi gamma invariant mass distribution is observed in the sum of the two control regions in order to estimate the background functional form directly from data. This in order to be independent from the Monte Carlo description of the background. And in the sum of the two signal regions in order to perform the fit for the extraction of the branching ratio of W to pi gamma. You can see here a distribution of the pi gamma invariant mass in the sum of the two lepton channels. An unbeamed maximum likelihood fit is performed and no significant excess is observed. So an upper limit is set corresponding to 1.51 in 10 to the minus 5 at the 95% confidence level. This is not the most stringent limit at the moment, but it can become, since, as you can see, this is a strongly statistically limited search. The last analysis I want to talk about is the one that brought to the evidence to WW production from double parton scattering. So by double parton scattering, we indicate those events where two hard parton-parton interactions occur within a single proton-proton collision. Studying same sign DPS where the two Ws decay into leptons is quite promising. And this because the same single hard scattering cross-section is suppressed at matrix element level. Then there is the absence of jets in the DPS WW production that can be exploited. And the two leptons also provide quite a clean final state as seen by the detector. The cross-section for such process can be written in a simplified way as I reported here, where A and B are the two single hard scattering processes, for example, the ones that I reported in the two diagrams. N is 1 if A and B are the same process, or 2 otherwise. And sigma effective is a parameter related to the extent of parton distribution in the plane orthogonal to the direction of motion of the protons. It has been measured at various hadron colliders, but with rather large uncertainties.
Riccardo, just to tell you have 2 minutes.
Yes, thanks. The dilepton final states considered are mu, mu, and e mu. A combination of dilepton and single lepton triggers is used, and at reconstruction level, exactly 2 leptons of the same charge are required with a moderate amount of missing PT. The leptons must come from the same primary vertex, and the event is vetoed if it contains V+jets, but it can be retained if it contains at most 1 non-V-tagged jet. Then 2 MVA classifiers are trained to separate the signal from the 2 main background contributions for this search. That is the WZ production and those processes with non-prompt leptons, so W+jets and QCD multi-jet, for example. The WZ production has similar lepton PT spectra with respect to the signal, but the bosons share a Lorentz boost along the Z axis, while there is no such correlation for the signal. For processes with non-prompt leptons, these have usually large cross sections, but also larger kinematic differences with respect to the signal. Then the 2 classifiers are combined and mapped into a 1D classifier, and the maximum likelihood fit is performed simultaneously on the 4 independent distributions of the final BDT classifier given by the 2 lepton flavors and charges. Here you can see 2 of the classifiers, but the other 2 are similar. Is the double parton scattering WW cross section that has been that has a significance of 3.9 sigma. So this is the first evidence for DPS WW production. But also these other 2 significances are reported, and they correspond to different calculations basically made with predicted cross sections with different hypotheses on the tuning of the Monte Carlo and on the input value of sigma effective. And these are pretty different, as you can see. So this is one of the reasons why it is important to measure the DPS WW cross section. And the last result is extracted from the fit is the sigma effective parameter. And to extract this, the single hard scattering cross sections come from theoretical calculation, while the DPS W cross section is the measure. So to conclude, I have presented some recent W boson measurements. First of all, the W boson rapidity, polarization, and differential cross sections is an impressive set of measurements and a fundamental step towards the precision W mass measurement. Then the search for the rare decay of W2 pi gamma, which somehow paves the way to new and effective search strategies for this kind of decays. The observation of more stringent limits at least will be accessible with LHC3 and future hadron colliders. And actually, the DPS WW cross section, this is the first evidence for this process. And on the side, it will have validation of the factorization approach used in Monte Carlo generators. And on the other side, it can provide more precise definition of contribution of this process in searches for new physics. CMS is a vast electroweak physics program. So the results concerning the W bosons are actually many more. If you're interested, you can see, for instance, our talk on VBS results on Thursday in this parallel, or you can take a look at our CMS public webpage. Thank you.
Thank you, Riccardo, for showing this new exciting results from CMS experiment for W boson measurements. Do we have questions, comments? Please raise your hands on Zoom. And just a reminder for people that in case you cannot find the raise hand button, if you click on participants, it should be on the bottom. But also let us know in chat in case you can't find it. All right, any questions? Thomas, please go ahead.
Hi, Thomas Jojo here. On slide 17, on this rare decays, you say that you require the presence of 2 V+jets in order to reduce the contribution from non-ttbar backgrounds.
The number of V+jet is actually an input variable of the boosted decision tree, so there is no, let's say, that cut on number of V+jets in the event.
Okay, I'm curious about whether you also take some kinematic properties of the V+jets into account, because the contribution from TWB production has quite a large cross section in this region of phase space. Is almost, I mean, of the order of 5 to 10% of the total ttbar background. So I'm wondering whether you consider either kinematic cuts on those V+jets to suppress also this, or whether you include it in the modeling.
Yeah, no, the only actual cut which is put on these V+jets is a cut on the PT that has to be greater than 25 G. So yeah, no further kinematic property of the V+jet considered.
Okay. I think maybe there is room for improvement.
Yeah, probably.
In this
probably.
respect. Thank you very much.
Yes. Thank you.
Okay, we next go to Graham. Let me try to. He needs to be unmuted. There we go.
Okay, so on slide 15, I was trying to understand this. Is there actually a lower limit on the branching fraction, or is this just this is just for a particular model? But I guess there's just some chance of fluctuations in just how a W hadronizes that leads to the potential of just a pi gamma decay, or is there always some new physics that's associated with a kind of two-body decay?
I'm sorry, I'm not sure I understood.
On slide 15,
yes.
you have a lower limit of 10 to the minus 9. And I'm
Yes.
trying to understand how this can happen physics-wise. Is this always a prediction of a particular new physics model? Or I imagine that just if you had some fragmentation fluctuations, it's possible to have this two-body decay without any really new physics.
Yes, yes. I also think that the same thing you said is the one. This is a very complicated. It is a complicated calculation in general because it requires basically it uses some QCD factorization approach that is not, let's say, very trivial to compute at higher orders than the leading order. So that's why the range is so imprecise.
Okay, thanks.
Okay, we have time for one more question, if there is one. All right, I don't see another question. Thanks again, Riccardo, for this presentation. I think you can stop sharing now, and we will go to Lorenzo Sestini, who will talk to us about electroweak and top physics in the forward region, having the LHD detector in mind. Riccardo, please start sharing your slides. And your video if possible.
I think I have stopped.
Yeah, Can you see my slides and also me?
Yeah.
Okay.
I can see the slides. Yeah.
Okay. Can you see also in full screen and also my arrow?
Yeah. Looks good.
Okay. Thanks. So good afternoon to everyone. I am Lorenzo Sestini, and I'm going to present the Electroweak and top physics measurements in the forward region of proton-proton collisions performed by the LHCb experiment. So before going to the measurements, I would like to introduce the LHCb detector. LHCb is a spectrometer, a single-arm spectrometer that covers the forward region of proton-proton collisions corresponding to a pseudo-rapidity between 2 and 5. As you can see here, this is a complementary phase space region with respect to ATLAS and CMS. LHCb is composed of a tracking system formed by a vertex locator, a dipolar magnet, and several tracking stations. Then it has also a particle identification system formed by 2 ring imaging Cherenkov detectors, 2 calorimeters, and muon chambers. Concerning the LHCb performance, it has a good momentum resolution from 0.4% to 0.6%. This is the resolution on the measurement of momentum of charged particles. It has an excellent identification efficiencies, performance. For example, we have a muon identification efficiency of 97% with a misidentification probability between 1 and 3%. LHCb can reconstruct electrons, also considering the Brim-Stralsund recovery. And it has also an excellent vertex reconstruction system that allows LHCb to tag B and C jets with the reconstruction of secondary vertices inside the jet cone. So LHCb initially has been designed as a B-flavor physics experiment, but all these features can qualify this detector as a general purpose forward detector. So there are several motivations for doing Electroweak top and jet physics at LHCb. First of all, the measurements of cross-section, production cross-sections in the forward region are important tests of the standard model. And they can be compared with next to leading order or next to leading order Electroweak and perturbative QCD predictions. As example, in this plot here, you can see this production ratio related to the ttbar production. This ratio is the cross-section initiated by Q bar or quark gluon initial state divided to the total ttbar cross-section. And this gray region on the right is the region accessible only to LHCb. So it is very interesting to probe these predictions. You can see, for example, here the scale uncertainty that we have in this region. It is interesting to probe this prediction with the LHCb detector. Moreover, these measurements provide access to Parton distribution functions in 2 different regions. In this plot on the left, you can see the Q square and X space. X is the Bjorken X, the fraction of the momentum taken by the parton in the hard interaction. And you see 2 orange regions that are related to LHCb, one at high values of X and one at low values of X. And this last one at low values is unexplored by the other experiments. Moreover, we can also perform precise measurements of several standard model parameters like the Electroweak mixing angle, the W mass, and others. So the physics program on Electroweak top and jets at LHCb is wide and rich. I tried to summarize it in these tables from the Electroweak boson, the direct Electroweak boson production, but also we have also measurements on the associated production where Electroweak bosons are produced in association with jets or heavy flavor jets. And we can also measure the top and heavy flavor production like ttbar, VB bar, or CC bar. Today in this talk, I'm going to talk about the measurements in green, sorry. So we can go to the Electroweak boson production. First of all, I'm presenting the measurement of Z production in dimuon or dielectron final states. We have a lot of these events, so we can perform differential cross-section measurements. And here I'm presenting some of them at 13 TeV. We require leptons with a transverse momentum PT greater than 20 GeV and with a dimuon or the electron invariant mass between 60 and 120 GeV. In this way, we can select high purity samples. For example, we have a purity of 99.2% for Z2 mu events and a purity of 92.2% for Z2 electrons events. We are currently dominating by the systematic uncertainty, in particular on the luminosity measurement, that is around 4%, but this is not a final calibration, so we can improve these measurements. On this plot here on the left, you can see the differential cross-section as a function of the rapidity of the Z boson for the muon final state in orange and for the electron final state in blue. On the right, you can see the distribution of the PT of the Z boson for the muon final state. All these measurements are compared with several predictions in black. You can see that they are in a fair agreement with these predictions. But we can also perform, as you can see here on the bottom right, a test of the lepton flavor universality by comparing the cross sections of the Z2 mu and Z2 EE. And they are compatible within the uncertainties, and they are compatible also with the prediction. Another decay channel of the Z that we studied is the Z2 bar. So in this channel, we select two heavy flavor tagged jets reconstructed with the anti-KT algorithm with a radius of 0.5. So heavy flavor tagged means that the jets contain a secondary vertex. In this case, we select the jets with the transverse momentum greater than 20 GeV and the jet invariant mass from 45 to 165 GeV. So the challenge here is to extract the signal from the overwhelming QCD background, and we define the signal and QCD enriched control regions by exploiting the Z plus recoil jet kinematic. We perform this simultaneous fit to these two regions, as you can see here, and by subtracting the QCD background from the signal region, we can obtain this nice Z2 bar peak. You can see here the jet this peak, the jet invariant mass distribution of Z2 bar events. The measured cross section is compatible with the next reading order prediction within the uncertainties. But we can also measure the Z2 tau tau decay. So here the taus are reconstructed in several decay channels. So in the leptonic decay channels, so in muon or electron, or in the hadronic final state, where we select one single hadron or three hadrons. So we define the 7 streams depending on the tau decay channels. For example, in this plot here, you can see the invariant mass distributions of tau pairs. On the left, for taus, the first one in the muon final state, the second one in the single hadron final state, and on the right, the mass distribution of tau pairs, where the first one is reconstructed in the electron final state, and the second in the hadron final state. You can see the data points in black, but also the predicted backgrounds and signal. The signal is in red. The signal yield is obtained by subtracting the data minus the expected backgrounds. So we obtain the cross sections for the different streams. The experimental uncertainty are dominated by the knowledge of the selection efficiencies and the background estimation. We obtain the cross sections in different streams depending on the decay channels, but then we combine them in one single Z2 tau cross section, and we compare these with several predictions performed with different PDF sets. Again, we can perform a test of the lepton flavor universality by dividing this cross section for the cross section of the Z2 mu or for the cross section of the Z2 EE. In both cases, we obtain one within the uncertainties. For the W, the easiest channel is the W2 mu. We did the W2 mu on plus neutrino, but in this case, I am presenting a more difficult channel, the W that decays in electron plus neutrino. In this case, in order to extract the W yield, we fit the electron PT distribution. As you can see here, this is the result of a fit. In light blue, the signal, but you can see also the backgrounds. Even in this case, we perform the differential cross-section measurement. You can see the cross-section of the W plus as a function of the electron pseudo-rapidity in orange, and the cross-section of the W minus as a function of the electron pseudo-rapidity in blue, compared with predictions. Electron universality tests can be done also here by dividing the cross-section of the W to electron to the measured cross-section of the W to muon, and again we obtain a result compatible with 1. Okay, we can move to the associative production, and here I present the measurement of the W or Z plus jet. The W and Z are reconstructed in the muon final state, and the jet is required to have a transverse momentum greater than 20 GeV. In order to extract the purity of the W plus jet sample, we fitted the muon isolation defined as the PT of the muon divided by the PT of the jet reconstructed around the muon. Of course, if the muon is isolated, this isolation is 1. In fact, in this fit here, you can see the result in blue. We have the signal that it is around 1, while the QCD background has different values. For the purity of the Z plus jet sample, this sample has an high purity, 97.88%. We didn't perform fit here, but we just subtracted the expected background. That is quite low. Then we obtained the cross sections, and the systematic uncertainties here are dominated by the purity determination and by the jet energy scale resolution. You can see here this nice set of measurements on the right. So for the W plus jet, the Z plus jet, but also the ratios between W and Z cross sections, or W plus to the Z or W minus to the Z cross sections. We measured also the asymmetry between the W plus and W minus cross sections, and we compared them with next to leading order prediction. You can see here we put both the scale uncertainty and the PDF's uncertainty in the same plot. You can see that they are compatible within 1 or 2 standard deviations, depending on the measurement. Then another measurement of associated production is the measurement of W plus 2 heavy flavor jets, so W plus BB bar or W plus TC bar, but with this sample we can also extract the TT bar cross section. This is not where in this analysis we select the W that decays in muon or electron plus 2 heavy flavor target jets. This is not the cleanest sample at LHCb to measure the TT bar production. I'll go to the cleanest sample in a couple of slides. By the way, here we use the machine learning, in particular a boosted decision tree, to separate the W plus BB bar from the TT bar, and another BDT to separate the B from the C jets. So we performed simultaneous fits to 4 observables: the jet mass, the BDT that separates the B from the C for both jets, and the BDT that separates the W plus BB bar from the TT bar. You can see an example of fit result here on the right. This is a particular subsample, the sample with the positive charged muon, where the W is reconstructed with the positive charged muon, but you can see the signals and also the background. So we corrected by the efficiencies, and we obtained the cross-section measurements that you can see here are compatible with predictions performed with MCFM. The uncertainties are dominated by the B and C tagging efficiencies, and I have to say that this is the first W plus C bar cross-section measurement at a Hadron Collider. This is a demonstration on how LHCb is good in performing measurements with C jets. So the last topic I'm going to present is the top and heavy flavor production in the forward region. So as I said before, the cleanest channel where we can measure the ttbar production is the dilepton final state, where we select one muon plus one electron plus one tagged jet. So here we used almost 2 femtobarn inverse of integrated luminosity, that it is not our full run-through sample. We have more data available. By the way, in this channel, we expected 5.6 background events, but we selected 44 events. So you can understand what I mean with clean channel. Here you can see the distributions of the mass of the electron plus muon plus B, and also the distribution of the pseudo rapidity of the B jet. You can see the points, the data points in black, but also the signals and the backgrounds are expected. And you can see that most of the sample is expected to be ttbar in the distribution in purple. Again, we subtracted the backgrounds, we corrected for the efficiencies, and we obtained the cross sections. The systematic uncertainty are dominated by the p-tagging efficiency, even here. In this case, the statistical uncertainty is in the same order of the systematic uncertainty. The statistical uncertainty is even higher with respect to the statistical uncertainty is even higher with respect to the systematic uncertainty, as you can see here. So we need to use the full run-through data set to reduce the statistical uncertainty, but also we need to work to reduce the systematic uncertainty. On the right here, you can see the measurement of the cross-section, the direct measurement in the muon plus electron plus B final state compared with next to leading order predictions, and also the extrapolated measurement in the full phase space. And you can see that the compatibility is with the prediction is within 1-2 standard deviations. Okay, the last measurement I'm going to present is the production of BB bar and CC bar dijet in the forward region. This is a new measurement presented for the first time here at ICHEP 2020. So in this measurement, we select 2 heavy flavor tagged jets, and we measure the differential cross sections as a function of the leading jet pseudo rapidity, the leading jet transverse momentum, the dijet invariant mass, and the absolute value of the difference of the rapidities of the 2 jets divided by 2, this delta Y star observable. We used the 2016 sample, and this measurement is dominated by the systematic uncertainty, so it won't benefit, now it won't benefit from the full run-through data set. In order to extract the flavor composition, we fitted these 2 observables with a 2-dimensional fit. So we have this X0, that is the sum of 2 BDTs. It is the sum of a BDT that separates the heavy flavor from the light flavor for jet 0 plus the same BDT for jet 1. And X1 is the BDT that separates the B from the C for jet 0 plus the BDT, the same BDT for jet 1. You can see the result of the fits here. You can see the signals, BB bar and CC bar, but also the backgrounds. And these fits are dominated by the systematic uncertainties on procedure and template modeling. The measured yields are unfolded for detector effects and corrected for selection efficiencies. The overall uncertainty is around 20%, and it is dominated by the heavy flavor tagging efficiency. You can see here the differential cross sections as a function of the 4 observables, for BB bar in red, for CC bar in blue, compared with PT8 prediction. This is a preliminary result that we are going to prepare also next to leading order predictions. You can see also the cross-section ratio, CC bar to BB bar, measured and compared with the leading order prediction here as a function of the dijet invariant mass. This is the first differential CC bar cross-section at LHC. Again, this is a demonstration on how LHCb is good with C-jets measurements. So this is my last slide. To conclude, LHCb has a wide and rich electroweak top and jets program. So the LHCb measurements can be used to test the standard model in the unique phase space that it is complementary with respect to ATLAS and CMS. we can extract from these measurements information on Parton distribution functions in a region that it is unexplored by experiments, by other experiments, and they also provide tests of the electroweak and perturbative QCD calculations. So for the ttbar measurement, this will benefit of the full run-through statistics, and it will be possible to measure also the ttbar asymmetry, and also shown for the first time this inclusive CC-bar D-jet differential cross-section measurement that has been measured for the first time in the forward region. Of course, we have more measurements. These will come in the future. So thanks for your attention. And okay, I'm here to answer to your questions.
Thank you, Lorenzo, for this nice presentation. It's always really good to see the wealth of electroweak and top measurements from the LHCb collaboration. Are there any questions, comments? Please raise your hands. While we are waiting, maybe I get started on slide 6. One thing I didn't quite catch for the luminosity measurement of 4% uncertainty. So these measurements are from a few years ago. But do I understand correctly that you would plan to, let's say, update the measurements with an updated calibration of the integrated luminosity?
Yes, exactly. So yes, actually, we don't have the final calibration. We have this 4% uncertainty, but the plan is to update them for sure. Yeah, we have this technique with the gas imaging combined with other techniques. So we are sure that we can do better than this, but we need time to perform this calibration.
Okay, and you would expect something like 1% or so uncertainty for the luminosity, or even better?
I don't know exactly. Yeah, I think we can go to 2%, probably also 1%, but I'm not sure about this.
Okay, sure. I don't see any hands connected, so I will use this opportunity to ask a couple more questions. If
okay.
Slide 12, when you were showing the cross-section ratios and comparison with the theory predictions, I was wondering which, maybe you said it on your slide, I missed it, which PDF are you using here to show these comparisons? And if you consider, if you've also looked at, I think it would be interesting to see a couple of different, let's say, PDF predictions for using different PDF sets, just to see how they compare to the LHCb measurements of W/Z ratios and W+ or W- ratios.
Yes, for sure, it will be interesting. Here we are using the NN PDF, if I remember well. And we are obtaining the uncertainty with this by reweighting with 100 PDFs replicas as usual in this kind of predictions. But yes, it will be interesting to test other PDFs sets.
Okay, and the final question from my side, I know there are people who are working on the W mass measurement in LHCb.
Yes.
Can you tell us how it is? When could we expect the measurement? How is the effort going?
For sure, you can expect the measurement. It is a very complicated measurement, for sure. LHCb is a particular detector. For example, we don't have the missing energy. So, but we can obtain a good measurement complementary that can be combined with Atlas and CMS to improve the uncertainty, thanks to the anti-correlation between the PDFs in the forward region and in the central region. So you can expect them soon. It is under its way.
Very good. Okay, any other questions to Lorenzo? All right, I don't see any hands raised. Thanks again, Lorenzo.
Thanks to you.
I think this was the last talk of the session. We still have a couple of minutes before we start the coffee break, or if someone has any, let's say, general questions or comments to all the speakers for this session, please raise your hands. One thing I wanted to tell you is that the Zoom technical assistant is the participant with the name of this session. So the top quark and electroweak physics, the host here. So in case you have later today or during this week, if you have some technical issues with Zoom, you can always ping the Zoom technical assistant. Okay, I don't see any raised hands. So just a reminder that we will start the second part of today's session in about 35 minutes. I believe it's 5:25 p.m. CERN time. For now, we have our coffee break, and you can, if you like, you can stay connected or to discuss further. I see G has raised his hand. Please go ahead, G.
Yeah, hello, this is Hiri. Yeah, I would have still a question to previous speaker as for the top and forward region. So is there a chance to update the measurement with a larger data set? Or perhaps is there a way to look besides the dilepton channel also to lepton plus jets channel?
No, we are going to update the measurement with the full run-through data set. We still need to reduce a bit the tagging uncertainty on the V+jets, but it is ongoing. So it is not just an idea, we are working on it. So you will see an update on that channel soon.
Okay, nice, thanks, looking forward then.
Hi, this is Maria. Can you hear me? I could not raise my hand.
Yeah, we can hear you, Maria.
Thanks. I also have a question following up on Gidi's question. At the moment, so the measurement that you presented is, well, the statistical uncertainty and the systematic uncertainty are more or less comparable. And it's dominated by the B-tagging uncertainty. Can you comment on the size of the modeling of uncertainty affecting the measurement?
Yeah, so the size of the B-tagging uncertainty is around 20%, something less. So we are trying to improve this uncertainty with new calibration samples that can be used to measure this, the B-tagging efficiency. So the plan is to reduce this uncertainty by a factor of 2. So the goal is to reduce the systematic uncertainty on the top ttbar measurement of a factor 2 and to use the full run-through dataset. That is 6 inverse femtobar. This is the plan.
And on the theory uncertainties, do you have any uncertainty associated to the modeling of ttbar in the forward region? And what is the size of this uncertainty?
So the size, yeah, we have the uncertainty related to both the scale and the PDFs. Actually, in that case, we don't have any plan to reduce this uncertainty. This is just what comes out from the standard generators, AMC at next in order and PAWEG. We don't have a specific study to reduce it.
Okay, thanks.
The uncertainty is in the same order of the measurement. Maybe, okay, I don't have any more the slides shared, but it is of the same order of the experimental uncertainty.
Okay. No, it will be very good to have the measurement with the updated data set soon so that we can compare or ideally in the future even combine with the Atlas and CMS measurements. That would be really good. Thanks.
Any? Yeah, go ahead.
Thank you, Bob. And how can I raise my hands? I mean, I see the Giri has raised his hand in blue color, but I don't find any button to raise my hand.
I believe if you click on participants, you should be able to see how to raise.
In my Zoom version, there is no button to put me, the raise my hand.
G, how did you raise your hand? I also don't see for me.
Yeah, so I clicked on participants list, and then so you get a pop-up window, and on the bottom right there's 3-dot expandable menu, which then opens for me as raise hand. Not sure. And try to share my screen. But if I share my screen, then I can't share the Zoom menu. So yeah.
Sorry, I just took a screenshot of this, Thomas here. Perhaps I can share my screen and just show where the button is. Perhaps you can find it easier then.
But sorry, somebody says that co-hosts can't raise hand in the chat.
No, it's just G was a co-host, and he's a co-host, and he was raising his hand. So
I think it depends very much on the setup.
So I'm sharing my screen in case you can see it.
Yes.
I'm not entirely sure whether. Yeah, this should be the picture. So can you see my my screenshot of the Zoom window? I have the list of participants on the right, and there are the 3 buttons here where if you click on them, it will show the option to raise hand. And I'm a co-host, and we also tried it with a person who is not a co-host. But perhaps all of this depends on the version of Zoom that you have.
Well, I'm running my Zoom on Mac, the Mac iMac, but I don't have any such button, raise hand.
Okay, I think it's fine if someone can't find how to raise hand, but the important is to ask questions and participate in the discussion.
yeah, same here. I don't see. For me, I also don't see it. But okay, in any case, Inky, you and I can unmute, I guess. So that's okay. All right. So one quick correction. I think earlier I said that we started. So we will start at 5:20 Stern time in about 25 minutes. It's not 5:25 as I said earlier. But other than that, I think we can start the coffee break. So I just wanted to thank again to all to the speakers and to the people who have questions, and hope to see you all at 5:20 in about 25 minutes. People can stay connected if they like to discuss further, but we will take a short coffee break. Thanks.
Yeah, thank you, and let's see each other in 20 minutes then.
Thank you.
Okay. Hello, everyone. Welcome to the second block of the Top and Electroweak session of today. This block will be dedicated to inclusive and differential top and single top, or ttbar and single top cross sections from Atlas and CMS. And we start by Denise, who will present us the recent ttbar and single top inclusive cross-section results from CMS. Denise, are you there?
Yeah, can you hear me?
Yes, very well. I will remind you when you have 5 minutes left.
Yeah, okay, I will share the screen now. And put it full screen. You see the slides?
Yes, very well. It might be that they are a bit cut.
Cut.
The lower part.
I see it now, yeah.
But
yeah,
I can see it.
You can probably, you don't see the slide numbers, right?
Exactly. Well,
yeah,
I can see the slide number. I don't know if everybody has the same or may have similar problem.
I see them when I move the mouse away from the base of the Zoom window and the bottom bar disappears.
All right. I mean,
can also do it like this if it's better.
That works, I think, for everybody.
Okay.
I think there are some options, on top. It says like view options and you can have fit to window or something like that. Maybe that helps.
I think this works fine.
So can I start or?
Yes.
Okay, so I'm going to present recent ttbar and single top inclusive cross-section results in CMS. Oops, sorry. Yeah, sorry for this. So shortly here, you can see my outline. So I quickly introduce the top-quark production at the LHC in general. And I will present two different ttbar inclusive cross-section measurements, both of them in the dilepton channel, where one is using a tau lepton. And I will focus on two single top inclusive cross-section measurements, namely the T channel and the TW production. And last but not least, I present the Atlas and CMS combination of the run-one single top measurements. So for differential top-quark cross-section results of the CMS experiment, please have a look at Georgios' talk later in this session. So in general, top-quarks are produced dominantly in pairs through the QCD interaction, followed by the production of single top-quarks through the Electroweak interaction, meaning that at run 2, around 135 million top-quark pairs and around 50 million single top-quark have been produced. So why are we actually interested to measure the ttbar inclusive cross-section as precisely as possible? So on the one hand, we can constrain different PDF predictions as well as alpha S and the top-quark mass. And also this process is a main background contribution for many analyses beyond the standard model. At 13 TeV, we have a theory prediction at next to leading order plus NN and L with a value of 832 picobar. And I'm going to talk about two dilepton analyses, both with the 2016 dataset. And you can see from the pie chart that these two analyses make up only 9% of all top-quark pair decays, but they are important to probe the lepton universality. So coming first to the dilepton channel with electrons and muons. So we are selecting events with isolated electron-muon pair, 2 electrons or 2 muons of opposite sign. And we then categorize the events according to the number of jets with PT larger than 30 GeV and the number of BTEC jets. So we have 28 different event categories in total. We extract the cross-section through the profile likelihood ratio fit in the fiducial region and then extrapolate to the full phase space using the acceptance from the event selection. So the fit observable used here is the PT of the additional untagged jet of each event category, which is shown in this histogram as an example. And the dominant uncertainties of this fit are the integrated luminosity as well as lepton efficiencies and choice of PDF. So in this fit, we obtain an inclusive cross-section of 803 picobarn with a total uncertainty of 4%, meaning that this result is compatible with the theory prediction, but also outperforms it because the theory prediction has only a precision of 5.2%. In this analysis, also a fit has been performed for the simultaneous extraction of the top-quark pair production and the Monte Carlo top-quark mass, using the same event categories of the electron-muon channel as in the main measurement. This time, the minimum invariant mass between the lepton and the selected BTEC jet is used as a fit observable in order to maximize our sensitivity on the top-quark mass. So here we have a similar cross-section result as before, with 815 picobarn and an uncertainty of 4.3%. And if we have a look at the top-quark mass result of 172.3 VGV, we see that this agrees well with previous measurements that have been performed. Last but not least, we can use the top-quark pair production cross-section result from this simultaneous fit in order to extract the top-quark mass and alpha S in the MS bar scheme using different PDF sets. What is basically done is to compare the measured top-quark cross-section with the predicted theory cross-section by using different PDF sets. On the left-hand side, you can see the different results for alpha S for the PDF sets, and on the right-hand side for the MS bar mass. You can see that 3 of 4 PDF sets agree well with the world average value of alpha S, and the similar pattern can be seen in the MS bar top-quark mass. Coming to the second analysis, which includes a tau lepton in the final state. This process is important to check the lepton universality in TDBAR decays. And also it is a background contribution for beyond the standard model Higgs searches, like for example, if a charged Higgs decays into a tau. So we therefore select one electron and one muon, one heteronically decaying tau with opposite sign, at least 2 jets, of which at least one is BTEC. The signal and background categories are defined using the kinematic jet properties, meaning that for each combination of a BTEC and 2 untagged jets, we calculate the distance parameter, which uses the top-quark mass and the W boson mass. So in order to obtain a signal event, we require this distance parameter to be at least 60 GeV, or did we have only one untagged jet, which can be seen on the right-hand side in the histogram. We perform a profile likelihood ratio fit on the transverse mass between the lepton and the missing transverse momentum in the signal-like and in the background-like event category separately for the electron tau and mu tau final state in order to extract our signal process. What we can see in the histogram is that the signal shape differs from the one of the dominant background process, which is the lepton plus jets TDBAR process, where one jet can easily misidentify it as a heteronic tau. So other sources of misidentified heteronic taus are W-jets and QCD multi-jets. And we have also some minor backgrounds with genuine heteronic taus coming from a single top TW or from Trellian. So on the right-hand side, you can see the data to Monte Carlo comparison of the fit variable. And the dominant systematic uncertainties are clearly the heteronic tau misidentification followed by the integrated luminosity. The inclusive cross-section measurement yields a central value of 781 picobarn, which is below the theory prediction, but it's still compatible with the theory prediction with an uncertainty of 8.3%. By calculating the cross-section ratio between this measurement and the measurement I just presented before, we can check finally the lepton universality. And we see that the result for the cross-section ratio is compatible to unity, meaning that we don't see any hints for the violation of lepton universality. Coming to the second part of my talk, which is the production of single top quarks. So these processes are in particular interesting in order to directly measure the CK matrix element VTB, and also in order to probe different PDF predictions by calculating the cross-section ratio between top quark and top antiquark production. What you can see here is are the results of ATLAS and CMS for run 1 as well as for run 2, and the NLO and NNLO predictions. And I'm going to focus on the T-channel and on the TW measurement of CMS at run 2 with the 2016 dataset. So coming to the T-channel, this is the most dominant production mode at the LHC. And as you can see from these two Feynman diagrams, for top quark and for top anti-quark production, you can clearly see that they are produced asymmetrically because of the flavor of the initial quark. So by calculating the cross-section ratio, we are sensitive to the flavor of the initial quark and therefore to different PDF predictions. And also by defining a cross-section ratio, we can reduce several systematic uncertainties arising from the cross-section measurements. You see here in the production the VTB vertex, meaning that by using the total measured cross-section, we can extract the CKM matrix element VTB. And in this analysis, the leptonic final state has been considered, meaning that we have a leptonically decaying W boson and a B quark from the top quark decay and a light quark jet, which is preferably emitted in forward direction. So for the event selection, we choose events with one isolated electron or muon and jets and B-tech jets with PT of larger than 40 GeV. And similar to the ttbar analyses, we define event categories according to the number of jets and the number of B-tech jets, meaning that the 2-jet 1-tech category is the signal category, and we have 2 dedicated ttbar background categories with 3 jets and 1 or 2 B-techs. For the event classification, as the signal is rather small, we use a boosted decision tree with 12 variables in total, which is trained in our signal category against all backgrounds. And the most important input variables are the absolute value of light quark jet eta, which is shown in the histogram above, the reconstructed top quark mass, as well as the invariant dijet mass between the light quark jet and the B-tech jet. On the bottom right, you can see an example of this BDT output where you can clearly see that the T-channel events are towards higher BDT output values. So this BDT output is not only applied to the signal category, but to all other event categories, meaning that we perform a maximum likelihood fit to all available BDT outputs in order to extract simultaneously the top quark cross-section, the top anti-quark production cross-section in the T-channel, as well as the ratio. Here, the systematic uncertainties are either included as nuisance parameters, meaning profiled, or externally through varied templates, meaning non-profiled. And such non-profiled uncertainties in this analysis are the modeling uncertainties of the signal. From the fit, we obtain a total cross-section value for the T-channel process of 207 picobarn with an uncertainty of 15%. This agrees well with the NLO prediction calculated with Heather of 217 picobarn. And we see also on the plot in the left-hand side that the cross-section ratio is 1.68 with a relative uncertainty of 3%, meaning that compared to the analysis with the 2015 data set, where we yield an uncertainty of around 13%, we observe a huge improvement. What we can also see in this plot is that we can compare it to different NLO PDF predictions, and we can see that our measurement agrees well with most PDF predictions. Last but not least, we can extract the VTB value using the total cross-section, where we assume an anomalous form factor for potential left-handed vector couplings, which is 1 in case of the standard model. And we can see with the value of 0.98 and an uncertainty of 7.4% that this is compatible to the standard model expectation of almost 1. So the dominant uncertainties in this fit for the cross-sections are modeling uncertainties of the signal, like parton shower scale and matrix element parton shower matching. While for the ratio, the signal PDF is an important uncertainty followed by the limited Monte Carlo sample size. Coming to the second single top analysis, the TW production, where we selected events with 1 electron and 1 muon of opposite sign and jets with PT larger than 30 GeV. We defined similarly to the previous analyses event categories using the number of jets and B jets, meaning that the 1 jet 1 tag category is the signal category, which is shown on the right-hand side. And we have two different ttbar control categories, namely 2-jet 1-tech and 2-jet 2-tech. As we have an interference of the NLOTW.
Sorry, Denise, you have 5 minutes.
Okay. As we have an interference between the NLOTW process with the ttbar background process, we apply the diaphragm removal scheme on our signal process. And we train two different BDTs, one in the signal category and one in the 2-jet 1-tech category, in order to discriminate the TW process from the dominant ttbar background. Therefore, for the maximum likelihood fit, we have three different inputs, namely the two BDT outputs in the 1-jet 1-tech and in the 2-jet 1-tech category, shown on the right-hand side, and also to the PT of the subleading jet in the 2-jet 2-tech background category. Dominant systematic uncertainties here are pileup followed by luminosity and the jet energy scale. We obtain an inclusive cross-section for this process of 63 picobarn with an uncertainty of 11%, which is compatible with the theory cross-section of 72 picobarn, which is calculated at approximate NNLO. Last but not least, we come to the Atlas and CMS run-1 combination of the single top-quark results, meaning that we use the best linear unbiased estimator method to combine 7 and 8 TV measurements, which are shown in black in this plot. And we can clearly see that all combinations follow the theory predictions. And we can also see that T channel is the most precise one, followed by TW and the S channel process. So for each measurement, we need to group the uncertainty source into different categories before we can combine them. An example is shown on the right-hand side in the table. And we also need to make some assumptions about the correlation between similar sources of uncertainties in different measurements. And here on the right-hand side, you can see the ATV combination of the T-channel process. And you can see that the theory modeling as well as uncertainties connected to jets are the most dominant uncertainties in these combinations. We can use the measured cross-sections to extract VTB by using the relation given on the slide. And for the VTB extraction, which is performed for each single top-quark production channel and in the overall combination, we include in addition theoretical cross-section uncertainties as well as the impact of a ±1 GeV top-quark mass variation. And on the left-hand side, you can see the correlations of all the input measurements in the overall combination. And we can see that the correlation is in all cases below 60%. So here's the summary of the results for the VTB extraction. We can clearly see that the AT-VT channel analysis contributes the most. And in all of these measurements, the dominant systematic uncertainties are the theory modeling and the theoretical cross-section. And we see in green the overall combination with a central value of 1.02 and an uncertainty of 3.7%. We see that we have no hint for anomalous left-handed vector couplings. And if we compare this result with the teratron combination, we have achieved a higher precision. So far for run-2, we have the latest VTB run-2 result in the T-channel process, which is presented tomorrow in Julia's talk. Coming to my conclusion, I've presented recent CMS ttbar and single top-quark inclusive cross-section measurements using the 2016 dataset. The precision error has been now reached, meaning that we can now challenge with different with theory predictions at next to leading order. I have presented two different ttbar dilepton analyses, one including a tau lepton in order to probe the lepton universality, and we see that this is conserved in the ttbar regime. And for the single top T-channel process, we have calculated the cross-section ratio, which helps us constraining different PDF predictions. Concerning the run-1 combination for the single top-quark cross-section, we see no hint for anomalous WTB couplings in the extraction of VDB. Currently, results with full run-2 data are in preparation, so stay tuned. Thank you very much.
Thank you very much, Denise. Also, thank you for staying in time.
Yeah.
Questions to Denise? Please raise your hand, and if in case you cannot, you can just intervene. Okay, Lisa, go ahead.
Thank you. I have a question on slide 17 in WT measurement. You are saying that largest uncertainties are experimental ones. What about the uncertainty related to the way how interference between TW and ttbar is treated? On the previous slide, you are saying that you use...
I can have a look in the backup because I must have the full uncertainty table in there. So in the modeling, actually, the ttbar, μr, and μf scales are the most dominant one. And for the diagram removal scheme, we have an uncertainty connected to the comparison between diagram removal and diagram subtraction of 1.3%.
Right, and that is, so how those uncertainties are determined? Sorry, I missed that. What's the procedure to determine the uncertainties?
I think that, I'm not sure.
Are they included in the fit? Are they constrained by the fit? What's the procedure?
So my intuitive guess, because I wasn't the main analyzer of this measurement, is that it has been sort of evaluated as nuisance parameter by replacing the nominal TW template with a TW template where the diagram subtraction scheme has been used instead of the diagram removal.
Okay, thank you.
More questions?
Hello, this is Francesco speaking. Do you hear me? Sorry,
Yes, very well.
Raising my hand. At least I don't find any button.
Yeah, no worries. Just go ahead.
Okay, thanks. I was wondering about the dominant uncertainties on your slide 7, the dominant uncertainty for the mass extraction. You see it's systematics dominated, but what is playing the large role? And also, this is connected to this. Is this a fit to what type of prediction? Is this a NLO plus PS prediction? I mean, are you
it's a fit on the theory prediction of NNLO plus next to leading logarithm, which is shown on slide 4 on top, where you can see the prediction.
So you have an NNLO prediction that is used here.
Yeah.
Okay, that's interesting. And the dominant uncertainty, where is it coming from?
You mean in the cross-section measurement or in the mass measurement?
In the mass.
In the mass measurement, oh, I hope I have it in the backup, but I doubt that because I only included the cross-section uncertainties there. No, they apply for both. They apply for both actually because it's a
referring to the
fit.
mass. Sorry,
yeah.
maybe I was not clear. Both as per.
Yeah, it must be the same uncertainty for both as indicated in the slide because it's a simultaneous fit between for the cross-section and for the top-quark mass.
Okay. All right. Okay, I want to dig a bit deeper in the paper to see how the unfolding is done and how the mass is extracted here.
No, wait. This is a nuisance parameter in the fit. There is no unfolding here.
Okay.
This is not a differential distribution from which you obtain the mass.
Right. So it's a template fit.
It's a template fit, yeah.
Okay. All right. But then for a template fit, it's not possible that you're using NNLO distributions because the template fit uses Monte Carlo.
The Monte Carlo.
You mean the Monte Carlo? The Monte Carlo is next to leading order.
I'm talking about what predictions you're comparing to the template. That's why I was a bit surprised well, more than a bit surprised. So it means that here in order to fit, you are fitting, correct me if I'm wrong, you're fitting a Monte Carlo prediction, right? You're fitting a fully simulated Monte Carlo prediction in which you have two parameters. One is
the Monte Carlo has been simulated in NLO, yeah.
Right, fully simulated in NLO, and this is the mass that is related to that NLO plus PS calculation. Okay, that makes sense.
Sorry I was a bit confused. I thought you meant the overall theory prediction.
Okay. Yeah, comparing to NNLO, that's more than fine. That's what we usually do. But in order to extract the information, you always okay. For the details of which systematic uncertainty is dominant in that case, I'll check. I'll check the paper a bit more.
So sorry, and to follow up on that, and you cut MLB at 160, right? That's the full range of the distribution that you're showing.
It should be.
Yes, this is correct.
Yeah.
Thanks.
Okay, any more comments or questions to Denise? Either by hand or by voice? If not, thank you again, Denise.
Yeah.
And we move on to our next speaker, Teng Jian. Are you there?
Sorry, I should have unmuted. Yes, hi.
So Teng Jian is going to tell us about differential ttbar measurements in Atlas. So if you can share your slides. Thank you very much. I will let you know when you have 5 minutes left.
Right, thank you very much, Marie. So first of all, I'm very grateful for this opportunity and very honored to present this work, which is the combination of contributions from many colleagues in Atlas. So we had a very nice introduction to the motivations for measuring top cross-sections from Denise already. I'd just like to give a slightly different perspective on what makes this a wonderful area for studying top-quark production. So specifically in 2018, the luminosity that the LHC was delivering allowed us to actually produce roughly 16 top-quark pairs per second. And this really means that the top-quark is no longer just a target for physics analyses, but it's even in a similar way to the Z become a standard candle for experimental calibrations. Of course, the rest of my talk will focus on the physics analyses. Speaking of the motivations for those cross-section measurements, I don't repeat the generic ones, but try to highlight a few of the important roles of top-quark measurements, emphasizing, of course, as already mentioned, PDF constraints, and the top mass is the key standard model parameter. And of course, there will be dedicated presentations on this, for example, by my colleague Serena later in the week. Personally, I find it really interesting to have the possibility to probe things like different radiation patterns, as illustrated at the bottom of this slide, which involve this quark that escapes confinement. And I think so there's a really diverse form culturally in terms of macroscopic tops. And in a similar way, the Atlas measurements that I'll present today celebrate many signatures of the top quark, represented not just by the 3 decay modes, but also by the evolving decay topologies of increasingly boosted top quarks. And these analyses will take advantage of the characteristics of each decay mode, such as the high purity of the dielectronic mode, as well as the ability to fully reconstruct both top quarks in the all-hadronic mode. The 4 measurements, which are at square S of 13 TeV, which I'll cover, are listed here, and including links to the public documentation. And these comprise inclusive cross-section measurements in the semi and dielectronic decayness channels, as well as differential cross-sections in all 3 decays. For your reference, this slide gives the definitions of the objects and the fiducial phase space for the various measurements at particle level, which apart from lepton transverse momentum thresholds, in these cases, for these, they're mostly motivated by the trigger. Everything else is kept as consistent as possible. So now I'm beginning with the measurements. And the first one is an inclusive cross-section in the lepton plus jets channel, the only one here with the full run-to data set of 139 inverse femtobars. Here and in all the presented measurements, we use Paheg and as the baseline matrix element generator with Pythia 8 as the parton shower. And this analysis selects events with 1 electron or muon, at least 4 jets, and applies cuts on the missing ET and transverse mass to suppress the backgrounds. This inclusive selection yields close to 7 million data events, which are split then into 3 signal regions based on the V+jet and jet multiplicities. For each of these signal regions, a different observable is chosen, and collectively the 3 are used as input to a profile likelihood fit. The 3 plots on this slide indicate the distributions compared between daytime prediction after the fit. And for the 3 signal regions, respectively, we use the aplanarity, the minimum lepton jet mass considering all lepton jet pairings, and the average delta R distance between the 3 jets in the hadronic top candidate. The profile likelihood fit yields a fiducial cross-section of 110.7 picobarns, and that translates into an 820 picobarn inclusive cross-section on which the uncertainty is just under 5%. Major contributions to the uncertainty and the constraints from the fit are shown in this plot here, where the colored bars indicate the impact on the inclusive measurement before and after the fit, while the data points indicate the values and the uncertainties on the corresponding nuisance parameters. So what you see is that the leading uncertainties are mostly of a theoretical origin. The dominant contributions coming from the shower model comparison of Pythia 8 to HOEG 7 broken down into the acceptance and the migration parameters. To highlight one other item, the analysis team assessed the impact of applying next to leading order corrections via a top transverse momentum reweighting, and this was found to have a non-leading contribution. For the next analysis, inclusive as well as differential cross-sections were measured with the 2015 and 2016 data set in the dilepton channel, where events with an opposite sign electron-muon pair and at least 1 V-jet was selected. You can see in the table event yields split by year and V-tag multiplicity. And in the plot, I highlight the signal region selection, which uses the 1 and 2 V-tag bins, which have simultaneously large statistics and good purity. Using these 2 bins in the V-tag multiplicity, both the inclusive and differential cross-sections are extracted by solving the simultaneous equations bin by bin in the case of the differential cross-sections. And these take into account, of course, the luminosity, fiducial acceptance, and reconstruction efficiency, as well as measurements of the V-tagging efficiency, including correlation effects. The measurements were made separately with the 2015 and 2016 data sets and subsequently combined with the best linear unbiased estimator method. And these resulted in a measurement of the 2.4%. This result agrees very well. So within 1 sigma with the next to next leading order and next to next leading log predictions from top++, with the experimental measurement being substantially more precise than PDF uncertainties on the prediction, which you can see illustrated in the ratio panels on the left plot. This inclusive cross-section is then used to indirectly determine the top quark mass, producing a measurement of 172.1 GeV when the PDF or LHC conventions followed. In the backup slides and in the paper, you will find also cross-section ratios of the top pair production cross-sections at various energies, as well as ratios to Z boson production. In addition, this paper includes differential measurements of the lepton kinematics. For example, in the left plot, you see that a strong evidence is observed of mismodeling in the lepton transverse momentum distribution, where for this measurement, in each event, both the electron and muon are measured separately. Double differential distributions were also measured. For example, the delta phi between the leptons in bins of the dilepton mass, as shown in the right-hand plot, And you can observe here an increasing trend in the azimuthal angle mismodeling as the dilepton system mass grows. Next, I move on to the fully differential analyses, first showing the measurement with 36 inverse femtobarns in the lepton plus jets channel. In this analysis, the events are subdivided into two sets based on the transverse momentum of the top quarks. For high PT tops, a selection is applied which requires one electron on muon, and in addition, one large radius jet of radius 1.0 with a transverse momentum of 350 GeV, reclustered from the radius 0.4 jets. And in addition to this large radius jet, a small cone jet is required. One VTAG is also necessary to pass the event selection, but it can be associated either to the electronic or the hadronic top candidate. And furthermore, MET requirements are imposed. Events that fail the boosted selection are then considered for the resolved analysis if they have at least 4 jets and 2 V-jets. For the resolved case, the pseudo-top algorithm is used to reconstruct the top quark decays for comparison to the particle level predictions, whereas for parton level comparisons, better precision is obtained using a kinematic likelihood fit for the reconstruction. The measurements are unfolded using an iterative Bayesian unfolding process. And, once again, both single and double differential measurements were made. And on this slide, I've picked out 2 normalized measurements. So on the left, using the resolved analysis, I showed the multiplicity of additional jets, in other words, those not associated with either of the top quarks. From this, you can observe that the nominal MC prediction shows a mild trend just within the experimental measurement uncertainties, which in turn are bracketed roughly by the alternative Monte Carlo predictions. The right-hand side of the slide shows measurements of the boosted hadronic top PT in bins of the number of extra jets, where we observe mismeasurement, mismodeling in multiple bins, notably events with either 0 or 1 extra jets or events with greater than 2 extra jets. Measurements were also unfolded to parton level, allowing, for example, comparisons to the absolute next to next leading order predictions. And these are illustrated on the left in the distribution of the mass of the ttbar pair. And we find that the NNLO predictions mostly improve the agreement with data in this case. In the boosted topologies, we show the same top pair mass distribution in different bins of the top transverse momentum, where varying levels of mismodeling are seen for the different generators. The final measurement which are feature is in the resolved all-hadronic channel, which has been a challenging but ultimately rather rewarding piece of work. The biggest challenge in this analysis is the large multi-jet backgrounds, which result in a very harsh trigger requirement, with the trigger and offline once in each selection, on top of which further cuts on the V-jet kinematics are used to further reduce the multi-jet background, as illustrated in the bottom plots in the purple histograms. In this case, a delta R cut on the 2 V-jets helps to reject gluon splittings, while combinatorial backgrounds are removed by requiring the B-jets and their associated W-jets to be close. Speaking of the association and the top reconstruction, there's of course a combinatorial ambiguity in reconstructing these all-hadronic events, in which a chi-square reconstruction was used to identify the best permutation of jets, resulting in good top and W candidates. The selected permutation has to satisfy W mass constraints on the 2 pairs of non-VTAG jets, in addition to a requirement that the triplet top candidates have similar masses, taking into account the resolutions on the candidate masses which have been assessed in simulations. In the preceding measurements, the dominant backgrounds could be simulated and entirely with Monte Carlo. Well, yes. Whereas in the all-hadronic measurement, the main multi-jet background has to be estimated from data, which is done with the so-called ABCD method. And this uses 3 background enriched regions with reversed cuts on the top candidate masses and on V-jet multiplicity. Using the one tag.
Sorry for interrupting.
Thanks. In the one B-tag bin, we extract the nominal background estimate, whereas a comparison to an alternate prediction from the 0 B-tag bin allows an assessment of the systematic uncertainties. You see from this table that the final selected event yields are small, even in comparison to the dilepton channel. But looking at the plot on the right of the jet multiplicity, you can actually observe that the 6-jet region is nearly pure in the all-hadronic system signal. As the jet multiplicity increases, and actually the combinatorics get worse, and this produces an increasing background contamination, but nevertheless, we have enough purity for precise measurements in events with up to 3 additional jets. So onto the results. The same iterative Bayesian unfolding technique has been used as in the lepton plus jets measurement. On this slide, I show the normalized cross-section for the PT ratio of the leading extra jet to leading top quark candidate. We can observe, for example, that the power plus Pythia 8 and AMC and NLO predictions in general tend to predict softer radiation relative to the top quarks than is seen in data. But a better agreement is obtained with the power plus Herwig 7 and Chopin predictions. The dominant uncertainty overall is from a normalization shift, which is observed in a comparison of different Parton shower and hadronization models, whereas the systematic uncertainty on the background is found to be significant but not limiting on the analysis. We also unfolded these with larger modeling uncertainties due to the substantial phase-space extrapolation. So you see here that there is a slope visible by I in the leading top transverse momentum distribution. However, considering the uncertainties, the breakdown of which is shown in the right-hand plot, this is not found to be significant. Finally, I contextualized the various measurements by presenting a series of comparisons of the differential distributions as measured by the different analyses. On the left, we find the average top PT measured at parton level, and we really observe complementary precision in the lepton plus jets and all hadronic resolved topologies, where I'd like to point out the transition at approximately 120 GeV, above which nearly twice the resolution is achieved in the hadronic mode. The right-hand side, the top right plot shows the same distribution measured in the lepton plus jets decay mode, comparing the boosted and resolved hadronic tops. Whereas the bottom right plot compares the agreement between data and power Pythia 8 for the subleading top PT and the resolved and boosted all hadronic decays. I'd like to point out that the impressive resolution achieved in the large radius jet reconstruction allows a really high precision for the tops with PT greater than 350 GeV while remaining consistent with the resolved measurements. And I'd like to finish by showing the results of various. Indeed, the left-hand plot was already shown by Denise, featuring the energy dependence of the inclusive cross sections with a zoom on the 13 TeV results in the inset. And these are replicated on the right, where both ATLAS and CMS measurements are compared with a number of PDF predictions, in general agreeing well with the NNLO and NNLO predictions. So far, the most precise single measurement is the ATLAS dilepton measurement as presented earlier. So to finish up, I hope I've demonstrated that ATLAS is achieving really unprecedented precision in inclusive and differential cross-section measurements of top hat production. We look forward to surpassing this with more targeted analyses on the full 1.2 data set. You can expect further improvements from developments in jet and missing key reconstruction, as well as flavor tagging. Thank you for your attention, and I'm open to any questions.
Thanks a lot for a very nice and clear talk. Questions? either raising your hand or speaking up. Okay, for your cross-section measurement in lepton plus jets in slide 9, do I understand? Sorry. Do I understand that you're constraining? So for the fiducial cross-section, you're constraining all the uncertainties in the fit. But what do you do when you extrapolate to the full phase space? How are you treating the modeling uncertainties there?
Okay, so actually in this plot, I show the constraints on the nuisance parameters as they pertain to inclusive measurements. And those have actually been determined separately. There's a slight difference in the impact for the fiducial and the inclusive extraction. But I think to answer your question, there are potentially constraints as well on the inclusive measurement.
Sorry, so you're constraining for the extrapolated to the full phase space inclusive cross-section measurement, you're also constraining the modeling uncertainties in the fit?
Yes, that's my understanding.
And how can you make sure that when you extrapolate these constraints that are typically done within your detector region apply?
I might refer to the...
Okay, maybe I can explain. So inclusive cross-section is measured in the fit as shown here, and also fiducial measured and based on truth information extrapolated to the full phase space. Of course, this extrapolation then is not constrained in any way. Uncertainties in both cases are quite compatible. Maybe with extrapolation based on truth information, it's a bit larger, but not much.
Okay.
Yeah. And this is actually quite obvious, almost, because the two highest ranked uncertainties is shower model acceptance and luminosity are not constrained at all.
Right. Right.
And this was how the analysis was designed. It's shower model inclusive acceptance by definition cannot be constrained. And this 3% uncertainty directly propagates into the inclusive cross-section.
Okay, yeah, that is fine. I didn't realize. Thanks. More questions? Now, I have a curiosity. Have you thought about, have you considered combining the differential measurements in the full phase space for the fully hadronic and the lepton plus jets results?
Right, that's a really interesting question. I think it's challenging to do so given that we have different binnings.
Yeah, that's clear. But have you even tried accommodating for some common binning that could make this, or have you thought about it? Would it make sense?
I personally have not thought about it up to now. I think it, no doubt it could be done thinking about the nature of the analyses were quite similar, as you probably observed.
Right.
It's probably possible. I find it hard to say how much we gain as there's sort of complementary sensitivity, but in different regions.
In any case, of course, you would gain more from analyzing the full run-to data set in the individual channels. are there any plans on ongoing measurements? Do we expect full run 2 differential measurements in these channels anytime soon?
Yes, you can certainly expect some. I mean, there are already active groups working on, I think, more than one measurement in the lepton plus jets channel. For the all-hadronic, it's a little bit more challenging, mainly due to the trigger acceptance. Now, I think if that analysis were more or less focused on the higher PT range, then there's potential to gain. The inclusive yield is not really going to improve a great deal from 2017 and 2018 due to even more tight trigger cuts.
Mm-hmm. Okay, thanks. Okay, any other questions or comments? If not, thank you very much, Teng Jian, for the presentation, and we move on to the next speaker, Georgios Bakas, who is going to tell us about ttbar and single top differential measurements in CMS.
Hello.
Are you there? Yes.
Yes, hello, can you hear me?
Yes, very well.
Okay.
Can you share your slides?
Yes, just give me a second. So can you see now?
Yes, very well.
Okay, so hello everyone, I'm Georgios Bakas. On behalf of the CMS collaboration, I'm here to present you the top quark pair and single top differential cross sections in CMS for the 40th International Conference on Standard Physics. So starting, this is an outline of the presentation. First of all, we will look into the top pair production measurements. More specifically, we will present a single differential top quark cross-section measurement for high PP-jets. Also, we will present a normalized multi-differential cross-section measurements and from the triple differential cross-sections, we will present the calculations of the strong coupling strength, the top quark pole mass, and the pattern distribution functions. As for the single top production, the differential cross-sections for both the T-channel and the W mode will be presented. Also, for the T-channel measurements, the charge ratios and spin asymmetries are illustrated and calculated. So, first of all, let's take a look at CMS at the LHC full run 2. That started 2015 and 2018. During run 2, full run 2, the LHC produced unprecedented event samples, almost 10 to the 16th proton-proton collision center of mass of certain TeV energy were produced. And during this period, the total integrated luminosity was found to be almost 163 inverse femtobar. You can see on the top right corner the comparison between the LHC and the CMS detector recorded luminosity. Also, almost 300 million, maybe less, top quarks were produced during this period, making us, you could say, top LHC a top factory. And on average, almost 34 interactions per bunch of crossing, as you can see on the bottom right corner. Now, the vast amount of data enables broad physics that can firstly probe standard processes and calculations with high precision, detect their processes, and explore a vast kinematic phase space. Now, let's go. One could argue, why are the differential measurements of the top quark and its properties so important in high energy physics? So, detailed studies of the characteristics of top quark pair production as a function of different kinematic variables can now be performed at LHC, provide a unique opportunity to test the standard model at the TeV scale. Furthermore, any extensions to the standard model may modify this ttbar differential cross-sections in ways that the inclusive cross-sections measurement are not sensitive to. In particular, such effects can enhance the sensitivity to possible beyond standard model effects, and a precise measurement of the ttbar differential cross-section has the potential to enhance the sensitivity and as well as to challenge the theoretical predictions that now reach the NNLO accuracy in perturbative QCD. Moreover, the differential distributions are sensitive to the difference between Monte Carlo generators and their settings, representing a valuable input to the tuning of the Monte Carlo parameters. We'll start by looking into the top quark pair measurements. The first analysis we're looking to probes the all-hadronic decay channel, where both W bosons decay into quarks hadronically for high PD jets. When jets are boosted, they have high PT over almost 400 GeV. The decay products are collimated, as shown in the cartoon you see on the right. The selection here is based on the construction of a neural network that discriminates signal from background using jet substructure properties. Our motivation here is to explore the kinematic region beyond the reach of the resolved analysis. And as for the measurements, we measure both absolute and normalized differential cross-sections at parton and particle levels with respect to top and top pair kinematic variables. On the top, you can see some of the results of this analysis for the normalized differential cross-sections at parton level. Starting from the left, you have the leading jet PT, and on the middle, you have the leading jet absolute rapidity, and on the right, you have the mass of the ttbar pair. In general, the results are compatible with theory, and there is no PT slope. And it's worth mentioning that there is an overall shift of order 35% in the total cross-section. The same analysis probes the lepton plus jets channel for high PD jets, in which one W boson decays into a lepton and a neutrino, and the other decays hadronically into two quarks. The selection here is based on top quark and B quark jet categories to distinguish signals from background. For the measurements, we measure both absolute and normalized differential cross-sections of both particle and particle levels as before in the hadronic channel. And the results are presented here both in parton and particle levels for the normalized differential cross-sections. On the bottom left, you have the parton results as a function of the top quark PD and absolute rapidity. And on the right side of the slide, you have the particle results as a function of the top quark PD and the absolute rapidity on the bottom. In general, the results, the differential distributions are well described, but all models overpredict the absolute cross-section for almost 20%. And move on to the top pair multi-differential cross-sections. In this analysis, both the double and triple normalized differential ttbar cross-sections are measured in the dilepton channel using 2016 CMS data. The selection in this analysis requires two opposite charged leptons, two jets, which at least one must be B-type. The motivation here comes that we have, from the ttbar cross-sections, we can use them, especially the 3D ttbar cross-sections, to extract the PDFs and constrain high X gluons, whereas we also can constrain fundamental standard model parameters such as the signal strength, the strong coupling strength, and the top quark pole mass. A quantitative comparison to several Monte Carlo predictions is presented at parton level, where data can reveal trends and can distinguish between predictions. For the triple differential cross-section specifically, their calculation constrains strong coupling strength, top quark pole mass, and parton distribution functions. Up to this date, this is the most precise result for the top quark pole mass. And also we extract simultaneously the strong subcoupling strength and the empty pole mass from a simultaneous feed. On top part of the slide, we illustrate the results of the double differential cross-sections. On the left, we have a distribution of the absolute ttbar rapidity in different ttbar mass ranges. The shapes are well described in general, except for the largest ttbar range, which is the last bin that you see on the top left plot. On the top right, you have the comparison of the distributions of the PD ttbar and the same ttbar ranges to the theoretical predictions. This distribution is sensitive to gluon radiation. All models describe data well within uncertainties, except for the MT5 plus Pythia, which predicts PD ttbar distribution in the last ttbar bin that it's too hard. Moving on to the results for the triple differential cross-sections. So we have on the top left plot the illustration of the triple differential normalized cross-section at parton level as a function of the absolute ttbar rapidity in different mttbar ranges and jet ranges, which is measured using two bins. We have 0 jets and at least 1 jet. And on the bottom left plot, we have the illustration of the triple differential normalized cross-sections at parton level as a function of the absolute ttbar rapidity in different mttbar ranges again, but now the n-jet ranges are measured using 3 bins. You have the 0 jets, exactly 1 jet, and at least 1 jet. For this measurement only, the Polhoek plus Pythia is in satisfactory agreement with the data. Polhoek plus Herwig predicts too high of a cross-section for a number of jets more than 1, while the MT5 plus Pythia provides too worse description of the mttbar distributions for exactly 1 jet. Whereas for the top left plot, we can say that all Monte Carlos describe the data well. So on the top right table now, you have the chi-squared values of and degrees of freedom of the measured cross-sections with respect to the predictions of various Monte Carlo generators. And on the bottom right, you have the illustration of the p-values that correspond to the obtained chi-squared values. From these values, one can conclude that none of the central predictions of the considered Monte Carlo generators is able to provide predictions that correctly describe all distributions. The best agreement with data is probably provided by Pohuk plus Pythia and Pohuk plus Herwig, with the first better describing the measurements that are probing number of jets and radiations, and the latter describing the ones involving probes of the PD distribution. We now continue with the extraction of the strong coupling strength and the top quark pole mass from the triple cross sections of the absolute ttbar rapidity in different m ttbar ranges and the end jets in two bins. To extract the strong coupling strength and the top quark pole mass, the measured triple differential cross sections are compared to fixed next to leading order predictions, and the measured cross sections are compared to NLO predictions obtained using different PDF sets, top quark pole mass, or strong coupling strength values. In the top left figure, you have the triple differential cross sections that are compared to predictions that are obtained using different values of the top quark pole mass, as you can see, with black, blue, and red. Whereas in the bottom left figure, you have the triple differential cross sections compared to the predictions obtained using different values of the strong coupling strength. So the values of the strong coupling strength and the top quark pole mass are extracted by calculating a chi-squared between data and the NLO predictions as a function of the input strong coupling strength or the top quark pole mass, and approximating this dependence with a parabola. The minimum of this parabola is taken to be the extracted strong coupling strength or top quark pole mass respectively. Now, the extracted at NLO values are compared on the right to the world average. On the top right, we have the extracted strong coupling strength, for which we use the top quark pole mass value of 172.5 GeV. The extraction allows a precise determination of the strong coupling strength, and as you can see, there is a significant dependence on the PDF we're using. Whereas on the bottom right, you have the extracted top quark pole mass, for which we use the strong coupling strength that's obtained from each PDF set. The extraction here allows precise determination of the empty pole mass, and unlike the strong coupling strength, there is no dependence on the PDF set. We move on. We know that from the triple differential normalized cross sections, from the end jet at least exactly 0 and at least 1, the m ttbar and y ttbar differential cross sections that are used. These are used in a simultaneous PDF strong coupling strength and top quark pole mass fit at NLO, together with combined Hera-inclusive deep inelastic scattering data. On this slide, we present the PDF with their total uncertainties that are obtained from a simultaneous fit on the PDF strong coupling strength and top quark pole mass, as stated before, using the Hera distribution this data and Hera this data plus ttbar data as a function of phi, where phi is the fraction of the proton momentum carried by a parton. In general, we can see reduced gluon uncertainty at high and smaller impact on other distributions via correlations in the fit. This brings me to the end of the top ttbar pair differential cross sections, and we move on with a single top quark differential cross section measurements. The first analysis we'll look into studies top quark in the T channel. More specifically, the selection consists of events containing single muons or electrons and 2 or 3 jets. As for the measurement, both absolute and normalized differential cross sections at parton and particle level are calculated with respect to the top quark PT, rapidity, and polarization angle, as well as with respect to the charged lepton PT and rapidity and the W boson PT from the top quark decay. It's worth mentioning here that unlike the ttbar productions, the top quarks in the T channel are highly polarized due to the vector axial vector coupling structure. So on the two top plots on the left, you have the parton level absolute cross sections that are illustrated as a function of the top quark PT and the cosine of the polarization angle. And on the right plots, you have the particle level absolute cross sections which are illustrated as a function of the top quark PT index cosine of the polarization angle, again on bottom. In general, the results are in agreement with predictions using various NLO generators and various sets of PDFs. The same analysis also presents the charge ratios as a function of the several observables, both in parton and particle levels. We can define charge ratio as the ratio of the single top cross section to the sum of a single top quark and antiquark cross sections. We measure it differential. Yes, thank you. We measure it differentially as a function of the top quark, the charged lepton, and the W boson kinematic observables. Specifically here, we have it as a function of the absolute top quark rapidity and the W boson PT at parton level and particle level on top left and on the right side of the slide. A general comment for the results is that in general, the shapes are compatible with theory. Here, we illustrate the calculation of the spin asymmetry for the single top in the T channel that are extracted using the polarization angle distributions. The spin asymmetry is sensitive to top quark polarization, and it is determined from the differential distribution of the polarization angle at parton level. So the spin asymmetry is measured in 3 channels, the muon, the electron, and the combined muon plus electron channel. You can see that all of these calculations within total uncertainty are compatible with the predicted value of 0.436 that's found using the Pauwels plus at NLO, which has an eligible uncertainty. And this table illustrates a breakdown of the systematic uncertainties. Minor systematics such as pileup have been grouped into the others category. We move on to the single top measurement in the TW mode. This analysis measures the single top differential cross sections in the TW mode. The main challenge of this analysis is that background dominates signal, with ttbar being the largest. The signal extraction is performed by subtracting the background contribution, which is estimated through Monte Carlo simulation. Both absolute and normalized differential cross sections are measured at particle level with respect to several variables such as the PD of both the lepton and the jet, delta phi of the 2 leptons, the invariant mass of the 2 leptons in the jet, the transfer mass of the whole system, the 2 leptons, the jet, and the missing energy, and the longitudinal component of the formed 2 leptons and jet system. On top, we present the normalized differential cross sections at particle level as a function of the leading lepton PT and the jet PT. As a general comment, one could say that there is fair agreement within the uncertainties with all used Monte Carlo predictions. In this slide, we saw the normalized differential cross sections at particle level. On the top left, you have the normalized differential cross section as a function of the delta phi of the opposite charged leptons, whereas on the top right, you have it as a function of the invariant mass of the opposite charged leptons and the jet. On the bottom left, you have the longitudinal system formed by the opposite charged leptons and the jet. And on the bottom right, you have the differential cross sections at particle level with respect to the transfer mass formed from the opposite charged lepton, the missing energy, and the associated jet. In general, there is good agreement between data and simulation, and we can say that the dominant uncertainties here come from the jet energy scale and jet energy resolution, which have a large effect in the background estimation. This brings me to my summary and outlook. We have presented the single differential ttbar cross sections both in hadronic and lepton plus jets channels using the 2016 CMS data with high PT jets. Here we can say that all measurements are consistent with the standard model expectation, with an overall shift of order of 35% in the hadronic channel and 20% in the lepton plus jets channel. As for the multi-differential ttbar cross sections, in the dilepton channel, we're in the dilepton channel using 2016 CMS data. And especially for the 3D triple differential cross sections, is the first extraction of such kind using ttbar differential cross sections. It's the most precise result of the extrapolation of the top quark pole mass up to this date. And we extract both strong coupling strength and the top quark pole mass simultaneously. As for the differential single top quark cross sections, the TW process using 2016 CMS data, we measure differential cross sections both absolute and normalized at particle level. And we have presented also the results in the T-channel process using 2016 CMS data, where we present normalized and absolute differential cross sections at parton and particle levels. And from that, we calculate the top quark spin asymmetry in both electron muon and the combined channel that's estimated from the differential cross-section at the parton level from the polarization angle distribution. Stay tuned for most CMS results. That was it. Thanks.
Thanks a lot, Georgios. Questions?
So just one, Georgios, is Francesco again. On your,
yes,
I might have more, but I'm still thinking about the first one. So on your TW cross section for the single top, what is the selection here? It's two, you can use 1J, 1B, 1J, 2B. Sorry, 1J, 1B, 2J, 1B, 2J, 2B. So what how many jets? How many?
Slide 16? Sorry, you said TW, that's why.
Yes, slide 16, yes. Yes, it is like, do you remember? I mean,
I'm not sure. I don't think I have it in the backup. I can look if you want, but I think I will redirect you to be more precise and just not to say anything wrong. I would redirect you directly to the physical analysis, the pass of this analysis, just to be sure and don't make any mistake.
Yeah, because here you have the uncertainties are okay, they're still significant, but
yes,
the R versus the S doesn't seem to be a dominant one. So you might be off the region of interference with ttbar.
I think here, though, the selection here is based on different analysis, again, in the same channel, if I'm not mistaken. They're using the same analysis in order to publish some of the results. But I think it's based on a previous analysis. And even in the past, you won't find many things about the exact selection. Maybe you can send me a private message. I can redirect you directly to the previous analysis for that.
I see many hands raised. Is anyone related to answering this question?
Yes, Maria, it's Victor.
Victor,
here.
Yes, please go ahead.
Yes, answering the question regarding this TW differential, the analysis is done in the 1J 1 tag region. It's in the lepton channel, EMU, and 1J 1 tag is slightly enhanced by between loose PT jets.
Okay, thanks. So then you're clearly not in the interference region. Thanks.
Thank you, Victor. Teng Jian.
Thanks. This was just actually along the lines of Maria's question to me. If I remember correctly, there were both boosted and resolved hadronic measurements of the top PT distribution from CMS. And what I was curious is whether there were any plans to do a more widespread measurements in the hadronic, well, specifically in the resolved topology.
You're talking about high PT jet. Sorry, I didn't hear correctly.
Sorry, maybe I should clarify. So for the ttbar,
yes,
you had the high PT, the high
PT
measurement, and I think I recall that there was at least an unfolded distribution of the top PT in both resolved and boosted channels. But to my knowledge,
yes,
a measurement of other differential distributions. Is that in the plans at all, or is it not really?
If I understood correctly, this is the unfolded measurement for the leading jet PT, for example. There is and also an analysis, ongoing analysis for the full run 2. That's for the full hadronic channel. As for, have I understood correctly your question? Because
yeah, I guess I'm curious about the scope of this, like whether it's going to be both top high PT and low PT and a wide range of differentials.
I don't know if you can combine any of this analysis because they probe a different phase space, and but there is for the high PT channel, hadronic channel, there is an ongoing analysis for the full run 2, and it's probing higher MTD bar, like up to 5 TeV, and even, I don't know if it's going to go for the leading jet more than 1400 GeVs.
Okay, thanks.
Any more questions or comments? We have quite some time still for discussion until the coffee break. So not only so if you have questions not only related to this talk, but to any of the other talks, any pending question or comment, please feel free to raise it here.
Shall I stop sharing? And
no, first,
okay.
Is any other question related to this one?
Yes, of course.
Nadja?
Hi. Yeah, I have actually a very small question concerning the previous presentation. Maybe it was mentioned and I didn't get it. Can you say what is the requirement on lepton isolation in the boosted analysis of Atlas? Is it like you don't apply any sort of isolation, or you require that it is non-isolated, or how is it performed?
Hi, thanks. That's a good question. I would have to check up on the precise isolation requirements, unless someone else who's connected can fill in. I would say that's certainly an isolation requirement.
To my knowledge, if we are talking about boosted measurement in lepton plus jets channel,
yes,
you have boosted top on one side, but on the other side you have normal top with normal lepton isolation requirement, with the standard lepton isolation requirement.
So you mean one top is boosted, the other one is not boosted?
Well, the other one, the normal selection is applied. Yeah.
Right. I mean, in the slides, I didn't. Okay, maybe it is too late to get back to the slides, but in the slides, I didn't see any isolation requirement explicitly. That's why.
Right. No. Well, I hope I don't mix anything, but because this analysis was done in the resolved and in boosted channels, basically in one go, the lepton selection was the same for resolved and boosted topology.
Yes, this is Francesco speaking.
Thanks, Francesco, for confirming.
Okay, and did it have any impact on the performance of the analysis? Because normally, I mean, one would expect that if you have one top boosted, the other one has to be boosted too, and then your leptons is probably not as isolated as you would expect in the resolved system. So using exactly resolved analysis on one leg, I mean, is it checked that how would be the effect on the performance of the analysis?
Well, you go to a region. If you look at the kinematic requirements, the kinematic requirements have an impact, of course, on the statistics that you will have, right? So you are in the region where one top is boosted, the other one is not so boosted, or not so close. And yes, maybe one could even do something that we were also doing in the past, which is use a shrinking cone for isolation, which is also another typical standard technique for the isolation. But overall, the selection takes into account to the fact that the two tops are well separated, the delta R is large, and between the tops. So you are going into that region where one top can still be boosted, and the other one still has enough separation that you actually resolve it.
I see. Okay, thanks.
But to me, it's not also clear what do you mean by the performance of the analysis? Effect on what? On uncertainties, on statistics, on what?
I mean, the very simple thing could be, okay, if I was actually thinking mostly about a condition, some condition that is in which you have both legs somehow boosted. But if you are in a phase space that one top is not boosted, then fine. Otherwise, I mean, if your leptonic top is also get boosted and you apply isolation requirement on the lepton, you would lose the acceptance in the selection.
Oh, of course, you are right. Yes.
Yeah.
But
Just for completeness, I confirm that the standard isolation is used, so it's not shrinking cone in this case.
Okay, Luis.
Sorry, I raised my hand a while ago. I think it was mostly already said. I was just going to comment on exactly that the if you're requiring the hadronic side top to be high PT, you don't necessarily have the leptonic side one. But if you do care about the very boosted phase space, and you also have the leptonic side being more boosted, a typical standard isolation criteria, that the efficiency of that typically drops drastically as you get to higher PT. And so in the analysis here from CMS, the so-called mini isolation is used, which has a narrower cone at higher PT to not be impacted by exactly that efficiency drop.
Thanks a lot. Any final question or comment? On any of the other talks? All right, so then I think we can stop the session here. Just want to remind you that we will have a discussion session on top production that involves ttbar, single top, and associated production later today, starting at 8:30. So I encourage all of you to join and participate. We will also have a couple of invited guests from the theory side. So it's your opportunity to ask what you always wanted to know about top production. So thank you very much. Thank you very much to all the speakers of this session block. And I think we can move to the coffee break and then reconvene with the next block at 19:05. Thank you.
Thanks.
Hello?
Yes, hello.
Hello, do you hear me?
Yes, we can hear you fine. Hi, Scott.
And, you should see me now.
Yeah, that's right. Perfect.
Okay, and I have the screen share ready to go, so it should be okay too. I can try it out here, but it should be ready.
Perfect, thanks.
Yeah, whenever you're done sharing, I can share mine. It's ready to go.
Yeah, we still have 2 minutes.
Do you know when you downloaded your version? Because I updated it a little while ago with some more precise plots.
Okay, we can do that for sure, but
it was a couple hours ago, but
yeah.
I'm not sure when you might have got them.
Did you say you can't share, or
I can share them, but I don't know if you need them locally or not.
All right,
But
so
I will be sharing them.
All right, but just in case, it's good, and thanks for the reminder.
The content is identical, but the plots are better.
All right. All right, we are back on time in the last session of today's first Electroweak, top Electroweak session. And we have several contributions. First, we'll start with KK Monte Carlo generator for precision electroweak physics at the LHC. So, yeah, Scott, if you can try to share our slides, and we're looking forward to it.
Here it comes. Let's see. Okay, I've started a share of the slides. You should see the title page. Is it working?
Yes, perfect.
Can you verify? Okay, so let's start. KKMC is a program that was originally developed for Z boson phenomenology and electron-positron colliders. And it includes exponentiated multi-photon effects. So typically, it was used for electron-positron to Z or a photon to a fermion pair or a quark pair, and any number of photons. It includes exact order alpha squared leading log, ISR, FSR, and that's initial and final state radiation, and IFI, which is initial final interference, photonic corrections. It also includes order alpha electroweak corrections via an independent DiZ 6.21 module. As used at LEP, it supports up to 1 TeV collisions with a LEP2 precision tag of, let me try to move this because it's in the way, 0.2%. The last version of the program, which was publicly released, is 4.22. And it includes support for parton level collisions with quark initial states. Right now, KKMC has two development branches, which I'm involved in both of them. One is KKMC-hh for the FCC-EE era. Basically, will be an upgrade of the LEP era KKMC. And also the KKMC-hh branch, which adopts KKMC to hadronic collisions. In this talk, I'll focus on the hadronic branch, which has been used so far in some WMAS studies and is presently being discussed in Electroweak precision group meetings involving forward-backward asymmetry studies relevant to measuring the Weinberg angle. So this talk will basically be an overview for those who are not familiar with the program, and will include illustrations from various applications that it's being used for, and also a few particular features will be pointed out. The basic structure is I'll start by talking about briefly the low-level Monte Carlo that generates the events, the beginning of the events, so that you end up with some quarks and a certain amount of photons that should be included with them, which is then fed into KKMC, which adds multi-photon radiative corrections. DiZ feeds into KKMC as well, adding matrix element electroweak corrections. And then everything can then be fed into a shower. Right now, it's actually compiled together with a Fortran version of Herwig and produces a final event. So schematically, that's the structure. To go through the various steps, the low-level Monte Carlo is something called foam. It's an adaptive Monte Carlo by one of our collaborators, Stasik Yadek. It generates the momentum fractions for the quarks and a photon radiation factor, which basically gives you the fraction of the available energy radiated into photons. It also generates a flavor index for the colliding quark. So 4 variables are generated for a general collision. Without ISR, you would have the collision occurring at a scale that's just determined by the quark momentum fractions. So I'll call that Sx, which is x1, x2 times s. And s here is just the general proton center of mass energy squared. When you add ISR, you also have to add a photon factor, which we'll call V here. And that reduces the collision scale to effectively 1 minus V times the quark scale. And then you put this into the Monte Carlo and calculate it to the desired precision. But underlying it all, you have to start with a crude distribution. And roughly speaking, the crude distribution that we start with is an integral over just the PDFs that you would have at the quark scale, together with an integral over the momentum fraction for the, if you want the energy fraction for the photon, and some factors that govern the YFS exponentiation structure. When you put in the actual ISR corrections, it's governed by these factors gamma, which have a big logarithm. The S factor here I should call Sx because it's actually the scale of the quarks. But so it's the log of Sx over the quark mass squared. And then this gives you a quark level crude distribution that's basically just a Born cross section with no electroweak corrections in it. This is the starting point, and then we add everything else on top of this. The first step is to make a foam grid that approximates this integral on a basically a 4-dimensional simplex, and then gives you a crude Monte Carlo distribution that's a basis for all of the weights that we generated later. The heart of the program is the KKMC module, which includes all of the photonic radiative corrections and imports the electroweak corrections from DiZ. So KKMC has 2 modes. The earliest mode that was programmed is called exclusive exponentiation. And basically, that was YFS resummation. Basically, soft photon resummation at the cross-section level. This was upgraded to something called coherent exclusive exponentiation, which was developed specifically for KKMC. And that would be an amplitude level version of the YFS soft photon resummation, that was introduced for better control over initial final interference. In this formalism, everything is done using amplitude level soft photon factors and amplitude level exponentiation, and then exponentiated initial final interference effects come in naturally when you square the exponentiated amplitudes, which already contain IFI and FSR, and then interfere at the quantum level in the squared amplitude. We'll talk a little bit more about IFI and how it appears later. But for now, we'll just say the KKMC is providing a set of weights. EEX and CEX weights are calculated in parallel. And so you can actually pull out various levels of calculation to compare them. The best weight is right now defined to be the CEEX order alpha squared leading log weight. The EEX actually has a slightly higher level. It has order alpha cubed leading log in it, but it does not support initial final interference, which is important for a lot of our studies. So if we separate the photonic corrections, there are 3 gauge invariant classes that you can discuss, and you can turn them all on or off independently in KKMC-hh to see what the effect of each of them is. Initial state radiation, of course, is radiation from the quarks. Final state radiation from the leptons, and IFI, the interference between initial and final radiation. And of course, we include in here both real and virtual photons when we're talking about any of these. The final state radiation is already widely available via the program Photos, which I think everyone is familiar with. And it, of course, shares an author with KKMC. That's no accident. The YFS structure in KKMC is also replicated in Photos. And right now, the 2 programs have a very similar, I would say, implementation of FSR. So what we're really adding in KKMC-hh is the other branches, the ISR, the ISR, initial state radiation, the initial final interference, and also the Dizet electroweak corrections to the matrix element. I should point out that there are other programs that can calculate these effects. I'm presently discussing all of this in electroweak precision group meetings where we're comparing the results of this program and ones with POHEG EW, MC Sansi, and to some degree Horus and ZGRAD 2, which also include, of course, electroweak radiative corrections in a hadronic context. So they're all involved in these studies. However, all of these programs have different approaches, especially when it comes to ISR, the initial state radiation. And this is the biggest thing that's really different in KKMC. Traditionally, ISR has been assumed to be factorized into the parton distribution functions and not requiring much additional attention. In fact, when people were mostly concerned about 1% effects, ISR was pretty much neglected. We are looking at things below 1% at this point. All of these studies involving the high precision Weinberg angle studies involve things we're talking about effects now at per mil and even fractional per mil. So we have to have very careful control over all of these effects. And at that level, you cannot neglect ISR. It is suppressed relative to the FSR, of course, because quarks have small charges, especially for the down strange, all the lower type quarks. These have very, very low charges. And most of the effect, of course, is coming from the up type quarks. However, it's not negligible. And at the per mil level, you definitely can see effects of ISR. One way you can see these effects is by changing the parton distribution function you use. There are now available a number of parton distribution functions that include QED corrections. If you're using a program that factorizes the ISR into the PDFs or assumes it's in the PDFs, and you want to have precision effects at this level, you have to use one of these QED corrected parton distribution functions. That's one of the things that has become clear in the recent discussions for the sine squared theta W measurements. You really have to include one of these parton distribution functions. The earliest was MRST 2004, but that didn't have real high precision. Nowadays, we have ones like the Lux QED and NPDF, which is the preferred one for the studies we're doing now. Also, CT14 has a QED version. And these are all things that would be combined with a traditional program that factorizes the ISR into the PDFs. KKMC doesn't do that. KKMC includes ab initio calculations of the exponentiated photon radiation from the initial quarks because the entire structure of the program is really based on this YFS exponentiation structure ported to the amplitude level. For that reason, and also because we really want to see from first principles, what would QED, really perturbed QED, what would it be predicting for the ISR? And then you can compare them to these other approaches and see what level of consistency you have. Well, in KKMC-hh, we have to use a PDF in which the photonic effects are absent, at least to the claimed precision of the parton distribution function. Now, is this true? Presumably, when I talked to Martin from MRST 2004, it is to the level that they were working. That doesn't mean it's absolutely absent. So you may have to do some tests to see, is it really giving you the phenomenology that's expected, or are there some assumptions embedded in the PDF that's inconsistent with the assumption that we're making? That could happen. I talked to one of the authors, in fact, the one who made the QED corrections to CT14, and he also says that the QED effects have been removed to the effect that they were able within the precision level of the PDF. Now, how reassuring that is, of course, I think is subject to testing. I'm not entirely sure what the status is for NNPDF, but we can do tests with it and look for consistency in places where we expect there to be consistency. And that's one of the things that I'll be discussing.
Hello, Scott. Just a reminder, I think you should slightly speed up because based on
the I'm getting behind schedule. Okay.
Yeah, thank you.
Okay. What's the end time for the talk? About 3 minutes, I guess. Yeah. Okay. So anyway, So anyway, I'm a little behind schedule. So with a little less talking, one of the things you see with our approach that you wouldn't see with the others is the effect of transverse momentum in the initial state radiation. You can see that in graphs like the one I have on the right. It's very little until you get to high transverse momentum for the lepton pair. But at some point, there is an effect from the initial state radiation. Where on the blue line, you see what you'd get if you just had a PDF. On the upper line, you see what you get from KKMC. The next slide gives a comparison between adding photons via Lux QED to the ISR and adding ISR from KKMC. Here we only have ISR. There's nothing else turned on. If we turn everything off, we get one cross section. If we turn Lux QED on, we get a different one. If we turn KKMC on, we also get a different one. So how do these compare? We find that in either case, turning on the ISR by switching out your PDF or turning it on using KKMC but using the ordinary PDF gives you about a 0.6% change in the cross-section. So it's per mil level, as we would have expected. Also, it's pretty much compatible. The two shifts are very similar in magnitude. I would say that's a sign of consistency. Now, the degree of consistency you need may depend on the context, but for most contexts, sub per mil consistency should be an adequate amount of agreement. One other thing you'll see is that the average value of the lepton center mass energy shifts a little bit downward, as you might expect, because you've radiated some photons, and both show very small, just a fractional MeV shift in the average value of MLL. Here's a picture of the graph. So here you can see that whether or not you add the ISR by changing your PDF out or use KKMC, you get a very similar effect, as long as you're looking at observables that integrate over transverse momentum. This is the rapidity distribution for the two leptons together. You can see here there's also a very small change in the normalization, both in the same direction as long as the rapidity doesn't get too large, but things start to diverge at very large rapidities. In part because you can't get those rapidities if you don't have the ISR the way we have it. Now, another thing we looked at, just to give a very quick description of recent results, is initial final interference and how it affects the angular distributions. Because initial final interference, unlike ISR, has a very strong angular dependence. You can see it in these graphs. The blue curve is what happens when you turn on ISR and compare it to what you have if you didn't turn on, IFI, initial final interference. ISR is the red curve. The red curve is relatively flat. It doesn't affect the angular distribution much, especially if you're around the Z boson mass, where initial final interference has a very steep curve. But you can see that the ISR is flat and almost zero. So ISR is not the thing you care about here, it's IFI. And this has to be modeled very carefully because it's a strong effect. This is one of the things that we add with KKMC-hh that can be compared with other programs that add the same similar effects, and then study how this might feed into phenomenology. Just a quick comment about DiZ. We use DiZ. I'm not going to go through the details here because we don't have time, but what it adds is corrections to this basic Born matrix element where you put in extra factors. So it calculates these extra factors. It calculates all the things that are colored on this graph. These come out of DiZ. We import them into KKMC. We don't use them like they're shown in this picture. We just put them where they would belong in KKMC. For the record, I put the input parameters, but we're not going to discuss them here. They're just for the record. We use an input scheme that's a little different from some others. So you can't directly compare these results maybe to the G-mu scheme or an alpha zero scheme without taking a careful look at what DiZ would do with these. We're also using a new version of DiZ. So if you were using the LEP version, I should point out that all these factors have shifted on the order of several times 10 to the minus fourth. It seems to be pretty much independent of angle though. So the angular dependence doesn't seem to be affected by any of these upgrades. And then the last thing I'll just mention briefly is that we have a parton shower. So the parton shower right now is Herwig 6.52, but we're working with Smiodek to actually incorporate this with Herwig 7, and presently working on the C++ interface of KKMC-hh so that we can integrate it more completely into Herwig 7 and work on upgraded showers for it. With the shower we have now, you can see some effects. I'm not going to discuss too much what the effects are because we're running out of time. Also, the shower slows things down, so I don't have the kind of precision with the shower that you see otherwise. But the shower does have small effects on the observables. Not much, as you would expect, because all it does is really shifts the kinematics a little bit. So anyway, that's it. For a brief summary, we have now brought the KKMC into the hadronic context with KKMC-hh. We do use ab initio treatment of ISR, which is non-traditional, but appears to be consistent when it should be, and gives you some freedom in looking at transverse momentum that you wouldn't see otherwise. Also, we will be upgrading the shower, partly by integration with Herwig 7, and also at some point, the KRK NLO shower, which Yodek and Smiodek have been involved in, which will bring NLO QCD into the mix as well, and give a basis for starting to look at more mixed electroweak and QCD corrections. So that's it.
Thank you a lot. Thanks for bringing yourself back on time. Questions, please. Try to raise your hand, and if you can't, then of course ask the question.
Oh, and if you have the slides, it has references at the end, and graphs on DiZ. That's not part of the talk, but anybody who wants to look, those are there.
Mm-hmm. Yeah, thanks for this interesting insight into depths of a generator. We experimentalists often use and take for something granted. So I'd have a question for applications. You showed the AFB application and studied variables like lepton PT and so on. So is there some ongoing integration of this generator to current LHC experiments? Do you talk to Atlas or CMS? Or do you plan to do so?
So far, they aren't using the program directly. We're participating in the precision subgroup meetings, and so they can give us things that they want us to run in these meetings. And then the various people who have the different programs try to get consistency and see what we can agree on. That's the level we're working at now. We do plan to make the program publicly available to anybody who requests it. And anybody who has used KKMC in the past will recognize the interface. It has pretty much the same way of setting it up as the Electron version did. So it's fairly easy to run and it is available publicly to people who want it. So far, only actually LHCb has been requesting it.
Right, I see. Thanks. I'll check the raise hands. Any question?
Can I ask a question? This is Arm. I couldn't wait. Scott, so this last comment that you had about the QCD shower that can be fed to KKMC-hh. So this is, let's say this way, what is the interplay with the ISR then that you have for the QED ISR? Would this also include the QED ISR, or this is completely
different?
Okay.
Basically what we would do is, the way we're doing it now is feeding it to the event record in such a way that you have the you have the momentum for the that you've generated for the muons, and you have additional photons. The photons really just sit there. So when you give them to the shower, the photons are independent of anything the shower is going to do. So all you do is you feed the fermions into the shower with the information that it needs to process them as if it had generated it in its own, for example, HWH DYP, if you're using Herwig, the old Herwig, as if it came from there. And then you process it as you would a native Herwig event. Then you get something comes out with shifted momentum, which is all it really does. Is you're looking at shifting the momentum around at this level.
Okay.
Thank you. Anything last question to Scott's talk? All right. Just a reminder, we also have the Mattermost. So please try to go there, try to get our track 4 discussion. You can put the questions for speakers. Speakers can then review later, and the discussion should live a bit there as well. Thanks, Scott, for your talk. And we move on to the next one by Sarah on Electroweak and QCD aspects in V+jets.
Hi, can you hear me?
Yeah. Hi, Sarah, we can hear you. We can't see you. If you can share your video, that would be nice, and slides, and let us know if you have any difficulties.
Okay, so hopefully you can see my video. I think my bandwidth is probably not. I always have trouble with sharing.
I see, no problem.
Can you see my slides though?
Yes, perfect.
Okay, one second, because I can't see what you can see yet.
We see your slides also with the thumbnails on the left.
Okay, so
this sounds pretty good. Looks pretty good.
Okay. Okay, so I'll just start. I can't actually see what you can see yet, but okay, never mind. So yeah, so this is a presentation on the Electroweak and QCD aspects for V+jet measurements in CMS. So to introduce, so the V+jets measurements are obviously, processes are obviously valuable benchmarks to test the standard model. They provide precision tests of higher order perturbative QCD and Electroweak predictions, and they enable us to validate or verify the theoretical calculations from the latest and greatest Monte Carlo generators. And in addition, they enable, some of these measurements enable us to constrain PDFs, which are of course very valuable inputs to cross-section calculations for instance, Higgs measurements and also beyond the standard model searches. In addition to their value in testing and validating the standard model, these processes are also backgrounds to a wide range of searches for new physics. So for instance, in particular, dark matter, supersymmetry, exotic Higgs decays, like the Higgs decay to invisible particles, etc. It's clear that in this new era of precision LHC physics, we will need to have a better understanding of these background processes in order to improve the sensitivity of our searches, since we're not going to be gaining a lot in terms of cross sections from higher central mass energies, etc. And so there will be some of these, the systematic uncertainties on these measurements are actually from the understanding of their background processes. And in order to increase the sensitivity to those searches, we will need to improve our understanding of these processes. So in the talk today, I'm going to be focusing on these particular measurements. This is the measurements outlined in the plots below. So this is the triple differential cross-section of the photon plus jets measurement, the Z plus jet measurement using the initial data of 2 inverse femtobonds, just over 2 inverse femtobonds at 13 TeV, the Z over photon ratio, in particular focusing on the high boson PT, the first explicit study of the collinear Z emission, so this is where you have a Z emitted very close to a jet, and the Electroweak production of W+2 jets. And these are all using 13 TeV with a range of integrated luminosity from 2 inverse femtobonds to 35 or 36 inverse femtobonds. The first one, so the triple differential cross-section measurement of photon plus jet. So this measurement directly probes QCD and is also very sensitive to the gluon PDF over a wide range of the momentum fraction X and the energy scale Q squared. This particular analysis used just over 2 inverse femtobonds of data. So this was the early run 2 data at 13 TeV. The dominant background here comes from QCD multi-jet events where you have a neutral hadron, such as a pi-0 meson, giving you an isolated energy deposit in the electromagnetic calorimeter. And this analysis uses a multivariate technique, so using BDTs to identify those prompt photons and discriminate between background and signal. And the photon yield is then extracted from the shape of this BDT distribution. So these two plots here, you can see, are for 2 different bins of the photon rapidity. And these show the BDT output for the signal template, the background template, which is the red line here, and the fit to those 2 templates, comparing that to the data. So you can see the data and the fit, the ratio between those at the bottom plots, and also the chi-square, and you can see that there's pretty good agreement between the fit to those templates and the data. So this cross-section is measured as a function of the photon transverse energy for a transverse energy above 190 GeV. This is mainly motivated, that this threshold is mainly motivated by the trigger efficiency, because the lowest unprescaled trigger for the photon has an ET cut at 175 GeV. And so it only becomes sort of above 90% or so efficient above an ET of around 190 GeV. The photon rapidity is restricted to the less than 2.5 region, and the rapidity of the highest PT jet is also less than 2.5. And so this measurement is done in 2 bins of the photon rapidity and 2 bins of the jet rapidity. And the measured cross-section is compared to the next leading order calculation from JetFox. So this plot here shows the measurement and the prediction as a function of the ET. And the 4 different curves here correspond to the 4 different rapidity regions for the photon and the jet. And this slide here shows those 4 curves earlier, but for the theory over the data. So these are the ratio plots, so you can see more clearly how well the measured cross-section agrees with the predictions. And so this is, again, for the 2 photon rapidity and the 2 jet rapidity bins. So this measurement extends the photon ET range from 300 probe by the 7 TeV analysis to 1 TeV here. And also, I think there's a factor of 3 to 5 improvement or increase in the cross-section with respect to that 7 TeV result. So you can see that in general, there's agreement within uncertainties between the data and the predictions, with the hatched band showing the total systematic and statistical uncertainties for the data. And for the low to moderate photon ET range, the experimental uncertainties are actually smaller or comparable to the theoretical uncertainties, and therefore there is the potential to constrain PDFs with this measurement. So over here we're showing the comparisons with different PDF sets for JetFox. And so all these colored lines here show the different PDF sets. And in general, any differences between these PDF sets are small. So they're within the theoretical uncertainties that are estimated, or within the total theoretical uncertainty that's estimated for the NN PDFs. And so you can see that the hatched yellow band there pretty much covers any differences in the colored lines. And so these measurements have only recently been included in global PDF sets, and so this measurement has potential to constrain the gluon PDF, and therefore I'm guessing that this will be likely be included in future global PDF measurements. So the next measurement here is a differential Z+jet. So this was it's an inclusive Z+jets measurement where the cross section is measured, is unfolded, and is measured as a function of the jet multiplicity, both exclusive and inclusive, the PT of the Z boson, the PT and the rapidity of the first, second, and third leading jets, the HT variable, which is just a scalar sum of the jet momenta, and the ZPT balance. So this is the balance between the PT balance between the Z and the hadronic jets that are recoiling against that system, which actually probes some of the soft gluon emissions and can constrain sort of the multiple soft gluon emissions that are implemented in the Monte Carlo generators. So over here is shown the unfolded data compared to predictions from the leading order and next to leading order prediction from MADGRAPH, and also the NNLO predictions from Geneva for the exclusive jet multiplicity and inclusive jet multiplicity. The leading order prediction here is only has a statistical uncertainty, but it's scaled to the NNLO cross section calculated from Fuse. So you can see that for the NLO predictions, at least the results are consistent within the experimental and theoretical uncertainties, and that's shown in the blue shaded regions of in the ratio plots. And the Geneva prediction is only available for up to 2 jet multiplicities, and so you can see that it's within uncertainties is pretty. It seems to be pretty consistent. So this slide shows the Z boson PT and the leading jet PT distribution with respect to the leading order MADGRAPH, the next leading order MADGRAPH, the Geneva predictions. And on top of that, for the leading jet PT, there are also available NNLO predictions from the NJET prediction. So that's only available for the 1 jet bin. And so you can see at the bottom of that plot on the right, the comparison with NJET as well. And in general, you can see there's the NLO prediction, the MADGRAPH prediction is pretty, describes the data pretty well within the uncertainties. However, there are some differences in the shape, but they're pretty they're sort of covered by the uncertainties. The leading order prediction, there's obviously differences in both the normalization and also the shape. And the prediction from Geneva for the Z boson PT, there is some discrepancy with the data, especially in the low PTZ region. So this shows the second and third jet PT. So again, very similar qualitative conclusions can be drawn here as well. So the NLO MADGRAPH prediction is perhaps, and the NLO prediction from Geneva describes them pretty well within uncertainties. And on this slide is the HT and the PT balance between the Z boson and the jet system. And you can see that the main discrepancies here are from the Geneva prediction for the PT balance, which is in these low to moderate regions of the PT balance, which are not really covered by the uncertainties. Okay, so moving on now to the ratio measurement. So this was the Z over photon ratio at 13 TeV. So this is a cross-section ratio of the Z and photon plus jets versus a boson PT for highly boosted bosons. So requiring the vector bosons to be above 200 GeV. This ratio can constrain higher order QCD and electroweak corrections, in particular the electroweak correction, which we know have variations at the level of tens of percents as you go to higher boson PT. And so they're particularly relevant because this ratio is an input in the estimation of the Z to invisible background in searches for new physics, in especially dark matter searches, and those for Higgs to invisible. And these electroweak corrections can really modify not just the normalization out in the tails, but the shape of these of the distributions out in as a function of the missing energy, for instance. And so this measurement is important not just as an interesting standard model measurement, but also for constraining these important backgrounds in dark matter searches. So the event selection is shown there. I mean, in general, what we're doing is focusing on the high boson PT region, and so both of the Z and the photon required to have a PT above 200 GeV. And the leading jet is required to be above 100 GeV. We're only considering the Z to muon channel here, with the two muons passing tight ID requirements.
Yeah.
So
that we should maybe move on a little bit.
Okay.
About five minutes to finish your talk.
Okay, sure. So this is the Z photon ratio compared to the leading order and next leading order predictions from MADGRAPH. So this is the first prediction. This is the first measurement of this ratio at 13 TeV, and we're actually probing up to 1.5 TeV in boson PT. You can see the ratio plot at the bottom, which shows that the next leading order prediction from MADGRAPH is pretty consistent within uncertainties with the data. The leading order again has been normalized to the NNLO cross section, but there is some tension with the data at very low boson PT. So this is the photon PT distribution. Again, we're probing up to 1.5 TeV in boson PT. And we're also comparing this to the JetFox predictions, the NLO prediction from JetFox, which are pretty much consistent within uncertainties. And although there is a general overprediction at the level of around 20% for high boson PT. So moving on quickly to the unfolded, the ratio distribution. So this is Z over photon ratio. So we expect this to sort of flatten out or to plateau at high boson PT once you're above the mass of the Z, well above the mass of the Z boson. And so you can see here the comparison between the unfolded data and the NLO prediction from MADGRAPH, and they agree pretty well within the uncertainties. There is a fluctuation in the data for the penultimate bin. Rather than that, there's good agreement within uncertainties. So the same measurement also looks at the collinear region for Z emissions. So this is where you have a Z boson emitted very close to a jet. And in order to enhance this category, what we do is to impose a high PT threshold on a leading jet. And so we have the leading jet is required to be above 300 GeV or 500 GeV, and there's no requirement on the PT of the boson in this case. And so you can see we look at the unfolded the unfolded distribution for the data as compared to predictions from theory for the delta R distribution, which is the angular separation between the Z and the closest jet. And over here, the region around pi, so around 3.2 or so, which is dominated by back-to-back production of the Z and the jets, and the region below. So the low delta R region is really dominated by this collinear Z emission. And you can see the unfolded data compared to the leading order and next leading order contributions from MadGraph for the two different thresholds on the leading jet, so 300 GeV and 500 GeV. So as you increase the threshold on the leading jet, you get an enhanced contribution from the collinear from this collinear region. Okay, so moving on to the last analysis. So this is the Electroweak production of W+2 jets. So this was done using the 36 inverse femtobands of data at 13 TeV. This is the first observation of this process at 13 TeV. The event selection requires a high PT, high PT jets and well-isolated lepton and a dijet invariant mass of above 120 GeV. And again, this analysis uses a multivariate analysis to separate the signal from the background, with the main discriminating variables being the dijet invariant mass, which is shown at the bottom, the pseudo-rapidity separation between the two jets, which is also shown, and the quark-gluon discrimination, also shown here, where you expect the signal to sort of reside in the high MJJ region and also the high delta eta region. So the signal strength is extracted from a fit to the BDT output distribution, where the signal is in the high BDT region. And this is for the muon, and it is done separately for the muon and electron channel, and then also a combined fit is done to both channels. The experimental uncertainty here is dominated by the jet energy scale and a correction that's applied to the MJJ distribution and limited statistical size of the Monte Carlo samples. Whilst the theoretical uncertainty is dominated by the renormalization factorization scales and also the signal acceptance. So the signal strength is measured with respect to the leading order prediction, and that's shown at the top, and also is measured with respect to the next leading order prediction. So this is measured separately for the electron and the muon channel, and I'm showing here the results from the combined fit to those channels. So it's at the signal strength is 0.91, and this leads to a measured signal cross-section of 6.23 with respect to the leading order prediction, which is consistent with the leading order prediction from MadGraph at 6.81. And the same is true for the next leading order prediction, which gives you a measured signal cross-section of 6.07, and this is compatible with the next leading order prediction from Powhag. Okay, so to summarize, presented measurements of the V+jets processes at 13 TeV with between 2 to 36 inverse femtobands of data. So these included the differential Z+jets measurement, the triple differential photon plus jets measurement, the Z over photon ratio, the collinear Z emission, and also the Electroweak production of W+2 jets. So these are a range of measurements that target a number of different topologies and that are now pushing into regions of phase space that were not accessible before. So this is, with the 13 TeV and the amount of data that we've collected so far, we're now pushing into the high PT regions and pushing into higher jet multiplicities. We're able to look at processes like the collinear Z emission, which were not really possible to do before because we were limited by statistics. So it's really a very interesting time to be doing these sort of measurements right now. Thank you.
Thanks very much for these very nice set of results. Question, please. Yeah, Tomasz, you have a question? Go ahead.
Hi, Thomas, you're speaking here. I have a question about the theory uncertainties for photon plus jet and Z plus jet, actually. If you could go back to your slide 5.
Mm-hmm.
So just to clarify, you have the scale uncertainty and the total uncertainty. Is the total uncertainty including the PDF uncertainties as well, or?
Yeah, exactly.
Okay.
Yes, this shows that the scale uncertainty sort of dominates over here.
Yeah, it dominates. Okay. Then on slide 6, I think you showed predictions for different PDF sets.
Yeah.
And you say there may be sensitivity on gluon distribution, but the variations between different PDF sets don't seem to be that large as compared to the uncertainty on the on data. So have you actually done, I mean, has anyone done a dedicated analysis to see what the pull on the gluon distribution may be from this data?
Yeah, so I think this is not true across the full ET range, but only for low to moderate photon ET, where the experimental uncertainties are either smaller than or comparable to the theoretical uncertainties.
Okay. Can I go on asking? I have more questions about uncertainties for PT as well. Okay, let me just go on. So if you just continue with your slides a little bit more for this ZPT, yeah, I'm quite curious about the comparison of Geneva and Amadgraph AMC and low predictions. So Geneva is supposed to have a higher formal accuracy, but in many of the bins, the uncertainties seem to be larger than in Amadgraph AMC and low. Do we understand why that is?
I mean, just looking at it, it does seem like the statistical uncertainty is actually quite dominant in some of those bins, especially the very low PTZ and very high PTZ. So this is the light green shaded, which does seem to be larger than the statistical uncertainty that we have from the MAD graph. So that's perhaps partly contributing to it.
It doesn't seem to be the case in all. I mean,
no,
I would.
Yeah. So in the middle range, it does seem to be the systematic and the theory uncertainty that's dominating, not the Monte Carlo statistics. I'm not really sure what part of the theory uncertainty is dominating here, whether what the breakdown is with respect to the factorization scales and PDFs, etc.
Mm-hmm. Okay. All right. Yeah, that's basically it. I just wanted to see those plots again and maybe try to see whether you understand why that is. And I think.
Yeah, I mean, I guess so. You're expecting that you would expect the theory uncertainty to be smaller there, just because it's a higher order.
Yeah, exactly. It's formal higher accuracy. I mean, there was another plot where you also compare against JetFox. So Malik and JetFox. I think it was on one of the following slides, and there it seems to be that the JetFox uncertainties are also a little bit larger as compared to Malik at AMC and LO. So I'm wondering whether in MADGRAPH, to some extent, the theoretical uncertainties may be underestimated for one reason or another.
I can make a quick comment about this. This is Arm's. Yeah, I think they're not making an comparison because the theory uncertainties that are included for MADGRAPH is just the hard matrix element scale variations. So if I'm not mistaken, there are no parton shower variations, for example, included here.
Yeah, that's right.
The resummation uncertainties are included in this case. So if we included the parton shower uncertainties in the MADGRAPH predictions, the uncertainties would have been much larger at low ZPT. I think we are just not comparing the same things here.
But I mean, in JetFox, for example, there is nothing concerning resummation to vary, is there? In Geneva, I imagine there is, but not in JetFox. Okay.
Yeah, it's true that in JetFox, I think we do only have it probably is more apples to apples in terms of that, we're just varying the PDFs and the renormalization scales.
Okay. Thank you.
Right. We still have a few minutes. Any question? I raised my hand too, but also leave other people ask questions. Anyone can ask a question. Really, a student, can be any question of any level. The speaker is for you. It's for you here. Yeah, I may have a question to slide 17, to the Electroweak production of W plus 2 jets. So in the stack, you also include the W plus jets produced in kind of standard way without the, I guess, single or doubly resonant vector bosons. So and then you also have the interference term, which I assume is the interference between the Electroweak and standard W plus jets production.
Yeah, I'd have to check whether, yeah, I mean, I'd have to check whether that's the interference between this and the, or whether it's the interference between the Electroweak W plus jets and the Drell-Yan W plus 2 jets.
I see. Because for me, as experimentalist, one can really think of this as a separate process, but actually it's not, right? There always is the interference. So maybe my question is more general also to theorists, whether they feel comfortable with us experimentalists trying to separate this process in a way, like looking into a corner of the phase space where it should be present, whether this is theoretically sound and yeah, I mean, appreciated by the theory community. Not sure whether Tomasz can answer that or any other theorist here.
I think in these processes, so these diagrams that you see there is the VBF approximation, right? And I think this would be the dominant production, basically, depending on. I mean, if you ask for two well separated jets, and I think the contributions to the S channel production are relatively small, but I don't know the numbers from the top of my head.
Yeah, sure. Would be nice to know what the interference term is, because that is a few orders of magnitude smaller. Okay, thank you. All right, thanks, Sarah. Thanks for everyone for participating in the discussion. And then we have to move to the last talk by Graham on Electroweak precision physics at the ILC. Perfect. We can see you. We can even see your slides. So thanks a lot, and go ahead.
Okay. Good afternoon for me, at least. This is a talk about precision electroweak measurements with ILC, with an emphasis on experimental measurement aspects, including the determination of the absolute center of mass energy and the use of longitudinal polarization. My talk focus will be selected electroweak measurements with initial stage at center of mass energy is less than 250 GeV. And there are frequent references through the slides to the references. So the overview is to, first basic physics motivation and orientation to ILC accelerator and detectors, some of the experimental issues, and then a focus on the W mass, left-right asymmetry, and WW measurements, and then summarize. So as now that we have the discovery of the top and the eggs, newer physics beyond that may continue to evade direct collider detection. And one of the questions is how best to sort of explore in such a regime. One approach is a flexible, broad and probing program of underlying dynamics, using things like W pair production and two fermion production at high energy, but also with high precision measurements of other parameters at suitable center of mass energies. And here, the polarized beams that the ILC, which is a strength of the ILC, can give essential insight. This physics case for future E plus E minus collider is well established, and there's a real opportunity to explore this physics in a not too distant future. So as you know, linear colliders are the only practical way with E plus E minus to go significantly above the top threshold. ILC has been under development for many years. There was an engineer design presented in the technical design report in 2013, focus on running between 200 and 500 GeV with upgradable to higher energies. This is, in recent years, there's been more of a focus on starting as soon as possible at 250 GeV with energy extendability to higher energies later. There's now an optimized design at 250. There's easily achievable running at the Z-pole, and the international ILC project is really now transitioning toward realization in Japan. So the ILC project is shown here schematically in terms of the accelerator layout. So this is for the 500 GeV configuration. It was described in detail in the technical design report shown here. It's the candidate site in the north of Japan is shown here, which is, this is a 50-kilometer footprint. And this, at 250 GeV, one would have plenty of Higgs production, and at higher energies, one gets more access to other production processes for Higgs, like WW fusion. And this initial 250 GeV stage has a 20-kilometer footprint, and so is relatively affordable if any of these things can be affordable. There are various detectors designed for ILC. They're described in the TDR, ILD on the left, SID on the right. I'll give you a little bit more details about ILD on the next slide. It's very much a detector designed around particle flow for hadronic jets. The quadrant view is shown up here. Very high precision momentum resolution, very good jet energy resolution, able to separate WW from ZZ. And because this uses a TPC tracker, DBX can be used for particle ID at low momentum. The overall run plan is something like this, where one would expect to integrate something like 2 inverse afterburns at 250 GeV, then 4 inverse afterburns at 500 GeV, also run at top threshold. And this is over a multi-year period, including upgrades in luminosity and energy. There's a future upgrade to 1 TeV potentially, and there's also options for dedicated running with polarized beams at lower energies. This illustrates the potential sharing of the luminosity amongst the different polarization helicity states, assuming this kind of absolute beam polarization. So one of the critical things is very much the measurement of absolute center of mass energy for things like absolute W mass, Higgs mass, etc. And here, the method of choice is very much to use the dimuon momentum method in dimuon events, where one constructs an estimator of the center of mass energy using the energy of the 2 muons and the net momentum of the muonic system, which is a proxy for the recoiling, in this case, assumed massless photonic system. And then with this, one can get an estimator that is close to 1, which is for example, anomalous running at 350 GeV, and the spread of this is related to the luminosity spectrum. And with this momentum-based estimator, one needs to be able to calibrate the momentum scale. One way to do that is to make sure one has a huge sample of Jape size. If one has a huge sample of Jape size, one can potentially get statistical uncertainty at the 1 ppm level. Understanding systematics at this level is a different matter, of course. But this is the basic idea of this method. So if one can run it as the Z-pole, then with this new design that we have, this is the expected luminosity spectrum, which is a full width half maximum about 500 MeV. With the anticipated integrated luminosity, one would have plenty of statistics to study very carefully, systematics associated with understanding this energy scale. this very much enables a broader program of electric measurements and provides high Z statistics for various other things too. So there's lots of fun questions to explore with this. Looking at this more carefully with the statistics and this root SP method, one would imagine that the well, with the momentum resolution of ILC detectors, one would measure this this quantity to 230 MeV per dimuon event, and so one can get a statistical uncertainty of something like 0.2 parts per million with this run. And in the same run, one can also measure the momentum scale with this 1 part per million statistical uncertainty. So the idea is that one could concurrently collect Z events, measure the cross sections and the symmetries, and also control the nuisance parameters associated with the initial state kind of in situ. So an overall momentum scale uncertainty of 2.5 parts per million is conceivable, given this and this basic limitation. But of course, it needs further study. For now, we're estimating something like 5 parts per million on central mass energy scale at the Z, and maybe 10 at higher root S. Polarized beams are used very much in lots of the physics studies, and here what one has to realize is that one ends up with different averaging over the polarization states. And if one takes data with the 4 different combinations of helicity states of the initial beams, electron and positron, one can, in the particular case where one has, for example, S-channel photon or Z exchange, basically solve for the 4 unknowns associated with this in terms of the unpolarized cross-section, the left-right asymmetry, and the absolute polarizations of the 2 beams. So adding polarization is something that one is able to kind of like measure from the data, sort of, so one gets more physics, but one doesn't really add difficult nuisance parameters. So moving on to W mass, this is an experimental challenge. The 4 most promising approaches to measure W mass at ILC are a polarized threshold scan, constrained reconstruction, the hadronic mass or elliptonic observables. The first method needs dedicated running near threshold, but methods 2 to 4 can exploit the standard program where one is also producing Higgs bosons. Most of these also require quite good systematic control of the center mass energy scale. So they're kind of like, they will have correlated systematics associated with that. The overall target is a 2 MeV uncertainty on the W mass. This illustrates the polarized threshold scan, where the idea is that one sits near threshold. This illustrates like a 6-point scan. At threshold, the cross-section is dominated by a neutrino exchange, so it's very sensitive to polarization. And one can choose this combination of helicities and basically enhance the cross-section by up to a factor of 3 compared to LEP, or one can reverse this and reduce the cross-section like here. So basically you can sit here, measure the cross-section and its root S dependence, and use the polarizations to basically also control the background level. So this is very robust. You end up being able to measure the polarization and the background in situ. An example fit is shown on the left here, where this is based on 100 inverse counterbar and 6-point scan as illustrated in the previous slide with these polarization assumptions. This reaches something like 4 MeV uncertainty in the W mass and simultaneously measures the backgrounds and the polarizations. Here, the assumption is 10 ppm on the central mass energy, which adds 0.8 MeV to the overall error. But this overall error here includes the experimental systematics associated with polarization and background. The main one is this background determination. Moving on to W mass measurements from higher energy runs, like for example at 250 GeV or at 500 GeV. On the left, we see the distribution for semi-electronic WW events of the reconstructed mass compared to the generator mass, illustrating the resolution on this. with a full simulation study that includes the background overlay. So this is in green. This study indicates a statistical uncertainty of about 2.4 MeV. This can likely be improved, but this is going to be difficult given jet energy scale systematics. We expect the best result in this channel to come from the constrained fit, which uses information from both Ws. And one expects to do better at 250 GeV compared to 500 GeV. On the right is showing some leptonic observables, one using dilepton pseudomasses in purely dilepton events, which shows quite a large sensitivity to W mass. Similarly, the lepton endpoints, both the high endpoint and the low endpoint, have sensitivity, more sensitivity at the high end. This has a statistical sensitivity of about 4 MeV for the at 250 GeV. This is an example of a measurement that is better at the lower energies. Coming to the left-right asymmetry, this is something that was studied initially a while ago. It's based on measuring the 4 different cross sections and extracting this left-right asymmetry from running close to the Z-pole. With these assumptions, one can get a statistical uncertainty of something like 1.7 × 10⁻⁵ with 100 inverse femtobarns. This is degraded somewhat by some of the control statistics needed for the luminosity and the polarization. And there's also the effect of how well one actually understands the center of mass energy relative to Z mass, and understanding the luminosity spectrum based on some assumptions. This is the kind of uncertainty one is looking at. This would be something like 3 × 10⁻⁵ with 100 inverse femtobarns. The off-cited value of the error on the weak mixing angle looks to be very well within reach. So if one actually is doing this left-right asymmetry measurement close to the Z, and one actually does have very good control of the center of mass energy, one will want to also improve on some of the Z line shape observables, where one measures the Z line shape and forward-backward asymmetries and left-right asymmetries as a function of center of mass energy, and also in the left-right polarized forward-backward asymmetries. With this polarized scan around the Z mass, the statistical uncertainties are below 100 keV. So this is really in a different regime, and so one can already with ILC luminosities have sufficient integrated luminosity to really explore precision Z mass, and have improvements on, for example, the Z width. Fully exploiting the ALR measurement likely involves both running at the peak and also measurements from a scan. At higher energies, the full structure of the WW couplings to photon and Z can be explored, particularly with WW production in a semi-leptonic channel. In the LEP parameterization with these 3 parameters here, we show here potential precisions on these observables. This is a situation in which, for example, one can construct very accurately with very good precision the scattering angle of a W- boson from these events where you can tag the charge with the lepton charge. And these studies are based on full simulation study with ILD and their extrapolation. These numbers are for the same integrated luminosity, given that the dependence is such that there's better sensitivity at higher center mass energy, and one gets more integrated luminosity at higher center mass energies, this will be much better at higher energies than at 250 GeV. But already with ILC 250, the precision is like 2 orders of magnitude better than LEP. So in summary, I think ILC can advance greatly our knowledge of electroweak precision physics. Polarized electron and positron beams are a unique asset, can deliver a rigorous test of a standard model, and explore new physics highlighted by top mass measurement and much improved measurement of W mass. This left-right asymmetry is one of the real targets that looks extremely promising. And there's also the scope for the best W mass measurements from standard ILC running at center of mass energies consistent with Higgs production. We've got very good ideas of how to control some of the experimental systematics associated with the center of mass energy, the polarization, and the luminosity spectrum. One key thing is very much to understand the momentum scale. This is enabled by a very high precision tracker, but also a very low material tracker. And this promises to open up precision measurement advances for the Z mass and Z width. Needs more study. Very much an accelerator is needed, and there are ongoing very encouraging developments in Japan. And this kind of physics discussed here benefits greatly from efficient running at lower center of mass energies, and that's now included in the accelerator design that starts at 250 GeV. And I have various references here.
All right. Thank you a lot, Graham. And I open the discussion. Questions? Raise your hand or speak if you can't. No question, really? So I think this is a really nice overview of precision electroweak stuff that can be done on linear collider. Maybe I missed it, but what is currently the most probable version of the starting energy?
250.
All right. Yeah, you go to the.
So this would be it. This would be at 250.
Yeah. So the other listed energies, so they're supposed to come as a choice at the energy upgrade, or there could be several upgrades?
So this. So I think it depends very much on the relative merit of running at the Z or at the W pair threshold. These lower energies one could imagine doing before this energy upgrade, given that one would have enough oomph in both power and energy to do these runs. But they benefit greatly from very good polarization characteristics, so they might not be what you want to do immediately. You might want to make sure you've developed the best possible accelerator configuration for doing these runs. This energy upgrade needs, in the configuration in which you start at 250 with a shorter accelerator, and then one has to lengthen the Linux to get to higher energies, then that means that there would be some time where you would be you might be able to fit in, for example, lower energy running in this regime. What energies one does start with and the overall timescale is determined somewhat by international partners. If one really wants to do, say, top measurements of here, it would be good to make sure that there was enough energy to do that.
All right, thank you. More questions, more general discussion on this, or the previous talks as well on?
Actually, there is two people who raised their hand. Aidan, you want to go first, or?
Good. Sorry. I guess Gregorio?
Yes. Hi, Graham. This is Gregorio. Just, I heard there is something moving this summer in Japan. Can you give us some update of what's going to happen over August, or?
Yeah, so there's, this is a slide from Tomohiko's talk that's in one of the other parallel sessions. There's work going on to kind of like put together international development team that starts right now, basically. An idea is to move towards a pre-lab. So that in more detail from Satoru Yamashita, the idea is that this international development team starts right now and puts together agreements between the different labs so that there's this pre-lab that comes together to finalize lots of the technical designs and stuff, while at the same time, in parallel, there are proper international discussions to kind of like work out the kind of project details and things. So it's very much, this is kind of like starting now, and we expect there to be a decision on this at ICHEP this week to move forward with this international development team.
Okay, thanks.
Thank you. And we have Aidan. Right.
Yes, hi Graham. So this is a question about the choice of tracker detector technology, but in relation to the precision measurements like the W mass and the Z mass. To control the systematics, is it important that the trackers are TPC rather than silicon based, or is that a second order consideration?
I think it's a second order consideration, to be honest with you. But I do think it's important to measure things like, as said on this slide, details of hydronization to be able to identify particle rates and momenta spectra. That feeds into reconstructing of hadronic masses and things. So I think a TPC has quite something to offer in terms of doing that better. We haven't shown categorically that it's absolutely necessary.
Okay, thanks.
All right, thank you. Looking at hands raised. So I think we are in general. Oh, we have Stano. Go ahead. Stano, I see a raised hand, but we don't hear you.
You have mentioned, I'm sorry, I was muted. You have mentioned the top quark mass measurement, but you have said nothing about the expected precision. What can be said on this?
Actually, somebody like Alexander, who's on, could probably say more than me, but the basic experimental precision is unlikely to be a problem. It's more a question of, as usual, interpreting the experimental precision in terms of a top mass measurement. From that point of view, the cross-section measurement at ILC, at the E+ and minus collider is particularly special, and we expect to be able to measure with statistical precision of order 20 to 50 MeV with the anticipated integrated luminosities. I think there's quite some issues to get the theoretical errors below 100 MeV.
But in this case, it is below lambda QCD. So it is not clear what we will measure in this case. Okay.
That's interesting. Any theorist on this? Okay, it doesn't seem so. Of course, we can also continue on Mattermost. There will be a replay session. This is a reminder to all speakers. So you should watch for questions on Mattermost, other channels, emails, of course. We encourage people to participate in discussions as much as possible. And yeah, it seems like we are getting close to the start of the topical discussion devoted to top quark production in about 3 minutes. So we have invited invited theorists to discuss this topic. So please do stay connected. We have 3 minutes, so you can fill these with a... Sorry? Yeah, so we have 3 minutes. You just feel free to stay connected, have a short break, and the discussion will start in 3 minutes in this very same Zoom room. Will be moderated by Maria and Tomasz, and we expect guests and theorists to discuss the production, including differential cross-sections and ttbar plus X. Any other comment? Okay, so many thanks to all speakers of today's 3 sub-sessions to this, I think, very nice and successful session. Looking forward to see many of you connected tomorrow, and yeah, but stay to the discussion in 2 minutes. All right, and we'll start the discussion in just a minute. We are preparing a slide to be shared, so just please be patient, and the slide and moderators will be right back on you.
All right, and welcome to the first discussion session of the Top and Electroweak track. As mentioned, today we will focus on discussing top quark production. So that involves ttbar and single top and also associated production, even though we will have the talks on the associated production later in the week, we thought it would be anyway a good opportunity to just start some discussion there that can then be translated or can be continued during the presentation of the corresponding talks, or even in the second top discussion, which will be on properties and EFT. So for this session, we prepared just 1-2 slides where we collected a couple of questions from other participants in the session, and we take the advantage that we have invited additional invited theory guests joining in for this session, so that everybody can feel free to ask whatever you wanted in addition to these initial questions that we prepared just to get started. Maybe before anything, we would like to ask if there is any remaining question to the talks that were presented before that you didn't dare to ask before. Maybe you want to ask now. We encourage anyone to ask any kind of question. There are no silly questions. I mean, we want to have this as informal as possible to profit the most. So if there is anyone that has any pending question before, raise your hand, or if you cannot raise your hand, just speak up.
Yes, thank you, Maria, for this nice brief introduction. I think at this point there is no reason raising hand. Just please speak up if there is anything to discuss. And as Maria pointed out, we try to collect some questions, which I'm sharing my screen. I hope you see it all, which are basically split into 2 slides. And these are a list of questions grouped by topic, and the questions come from various experimental colleagues that we had the chance to sort of probe in a past day or so. But please don't feel limited by these questions in any way. These are basically just sort of seeds to start a fruitful discussion, which can go in any direction that we please. By we, I mean all of us participants of the discussion session. So I think you can see the discussion on the screen now. Maybe we should just leave you some time to read over them. If anyone feels particularly about the questions on the slides, feel free to ask them. If you have other questions to add, write them in a chat, or just let's. There is no real plan. Let's just try to discuss. So unfortunately, my list of participants doesn't show any participants while I'm sharing the screen. So if there is anyone who wants to speak up, then just please do.
So maybe we can just directly start with the first part, seeing that we have a couple of experts on calculations of top at NNLO QCD. So maybe one of the things that we were wondering, or one of the things that we wanted to figure out is if so this is addressed to the matrix authors in particular. Can the generalization of the QT subtraction method be applied to other processes involving top quarks like single top or TW and TTWZ, etc.?
Can you hear me?
Yes, very well.
Great. Okay. Yes. So yeah, the answer is yes. So as it is, so with the ingredients that we have right now that we used to do the calculation for ttbar production, it's not there yet, but it is possible to extend it. Actually, I think the extension for single top TW should be relatively straightforward. For TT plus some colorless final state, like TTV as it's written there, it's a bit more work, but it's I think it's certainly doable. So I would say it's still not there yet, but I don't think the subtraction will be the bottleneck for doing this calculation. Will probably be the two corrections. So yes, can be extended.
Yeah, that's fantastic news. Do you already have a timeline in mind? Are people assigned on working on this yet, or is this I mean, is this near or far future, or?
So I would say probably single top. It's probably could be near future. I think could be ready. It depends on the urgency, but maybe it could be ready for this year. I would say TTV. I don't think it takes that. So it depends on the manpower, right? That one decides to put on these projects. But I think TTV also could be done in I don't know if by this year from the subtraction point of view. But yeah, if not for next year for sure. But it really, as I said, it depends. So I think it can be done in a more or less straightforward way. We know what we have to do. It's just some time that we need to spend to do it. So it depends on how much time we spend on doing it. But yeah.
Will this also include decays?
So again, from the subtraction point of view, like doing TT, so ttbar production with decays would be, for instance, to include in the first step the decay into a V and a W will be, from the subtraction point of view, equivalent to doing TT plus TTV, for instance. So from the subtraction, this would be the same. But then, well, of course, if you, so there the bottleneck is a different one, right? Of course, if you want to do ttbar including decays, that next to be in order. So we are working on the ttbar code to include decays. I'm not personally involved at the moment in that project, but on ttbar including decays in some approximation. But for this, I don't have details on how this will be ready or not.
Okay. Fabio, you don't need to raise your hand, just intervene whenever you want.
Okay, thanks, sorry. No, I had a question for Javier, just a clarification. I mean, T-channel single top in the 5-layer scheme, I think is certainly doable. But I'm not sure I understood what you mean by having ttbar V and TW done by the end of the year. I mean, there are no two-loop 2 to 3 metric silence for this process.
Yeah, sure. Yes, maybe I said it too quickly, but I said from the subtraction point of view, this can be done. Like we can have the subtraction ready, and then of course the bottleneck is to have available the 2-loop that I think is indeed the most difficult part. So I was only talking about the subtraction.
Okay, we got very excited.
Okay,
yeah,
and thanks for the question then.
Yeah, I guess from the experimentalist point of view, when they ask this question, they want, I mean, I guess they mean, well, if there is a code, right, that computes it. I mean, in addition, for TW, there is this issue of the overlapping with ttbar, right? Already next reading. So I guess this would open up something that next reading has to be understood. So it's not a question only of the subtraction, I guess, no? I mean, it's a complicated story.
Sure. I just answered the question that is written there. Can the generalization of the Gitti subtraction be applied? The answer is yes, and so it's not available yet, but can be extended in a more or less straightforward way. But yes, of course, I fully agree with you, Fabio. There are more subtleties in order to have actually an NLO prediction. Yeah.
Thanks for the clarification.
No, sure. Thanks for the question.
And is there priority in when releasing these calculations? So it's a prioritized list. So when can we expect what, more or less?
Okay, now so for these other processes, I cannot give. So as I said, as we just discussed with Fabio, there are some ingredients that are still missing, and I don't know when they will be ready. For the ttbar code, this is already, so it's already available upon request. I think it has been already distributed among Atlas and CMS colleagues. But for the rest, I don't have an answer.
Maybe a follow-up question to David. I see him in the list of participants. So you also worked on this combination of NNLO QCD corrections with NNLO Electroweak. I mean, do you see this to be applied to different processes? Say, I mean, could this be readily available for combination with other NNLO QCD corrections in the top sector?
Can you hear me first of all? Because I don't know if
yes.
Yeah. So in general, definitely, if you're able to calculate the NNLO QCD, you're able to calculate the NNLO Electroweak, or more general, the complete NNLO that, for example, for TTW has been shown to be important. You can definitely combine the two calculations. There is a clear way to combine them. What you cannot do for any processes is the treatment that has been done for ttbar. In the case of ttbar, what we did in our study when we combined the NNLO QCD and NNLO Electroweak correction, we used this so-called multiplicative approach, in which you try to estimate further effects of mixed QCD Electroweak at NNLO. The way of estimating with the multiplication of K factor is not working for any processes. So one has to investigate, and case by case, process by process, and distribution by distribution, one can evaluate this. But definitely for this process that you mentioned here, the possibility of calculating NNLO Electroweak is already there, and they are already available. And once the NNLO QCD is there, one can even combine them. What I can say is that already for these processes, that is TT in association with a vector boson, W, Z, or in association with X, what we already did is combining the force together, not with the NNLO QCD calculation, but NNLO QCD matched to NNLL prime, NNLL, sorry. And so we already have given predictions that are more accurate than just NNLO. It's in the direction of the NNLO precision. So this, what you asked is already been performed, not exactly as you asked for this process. And two different groups I already did this kind of effort for the associate production.
Excellent, thank you. So then we also had a little bit more specific questions for the top production in association with other particles. So from an experimental from an experiment, it seems like the measurement of cross sections of TTW within TTH searches seem to be quite a bit higher as compared to theory predictions. And we also have a plot related to this, but I didn't include it to these slides if we want to discuss technical details. But first of all, has anyone been looking at this comparison with data, and whether the tension could be resolved by I mean, whether tension could be resolved, period. Okay, if no one has a comment about this, perhaps we can come back to this
Maybe I have a comment on this if nobody, because I didn't know if Ioannis Tsinikos was connected or not, because he worked in this direction. But what I can say is that I don't think, I may be wrong, but this is my impression, that it's not the lack of NNL OQCD correction here that need to explain this difference between the data and theory prediction, precisely because you see deviation from experiment and prediction only when you look TTW in the TTH context. When you look TTW in the TTW measurements, you don't see this problem. So there must be something really in the event selection that is pointing to this.
So I would tend to agree with that if you would see it only in one analysis or only in one experiment. But the fact is that even both Atlas and CMS, even if they have slightly different selections and slightly different ways of doing the extraction of this cross section, they see consistently higher cross sections than the available calculations. And there are many different possible calculations, and so we would like to understand what is missing in the calculations that can be causing this difference, or which calculation should we be comparing to from the available ones?
For example, you see what we already have shown is that when you do the calculation of this complete NLO to TTW, that this means not only an NLO electroweak correction, but even more something that is supposed to be subleading instead is important, and this 50% that you see there would be even larger if we didn't include that effect. Now, combining this with the extra radiation of QCD, so now I want to do a full-fledged simulation with not only TTW, but with the decay, and including also the TTW with addition the radiation. And in the case in which I add the radiation, I also consider this electroweak effect is very complex, and it's something that was explored, as I said, in this work done by Ricard Fredericks and Ioannis Tsinikos. But so rather than the hard NLO-QCD, there may be some effects related to multiple radiation of parton and electroweak effects within this that still may be explored, for example, in the context of effects, and this could be an explanation. This is what I'm just saying, that there's not only an NLO-QCD, there are other things that are still open and be investigated. And in my impression, this could justify why you see this deviation in the TTH analysis and not in when you measure TDW. If I'm not wrong, you see this deviation even in 4-top, but I may be wrong. Yeah? But if it was the NLO-QCD, I imagine you see it in general, not only for a specific analysis.
Well, I'm sorry, just one comment to add. First of all, it's not only TTH multilepton, it's also 4-top from Atlas, the latest measurement. And the last measurement of TTW comes from 36 femtobarn data set. Very small, with large uncertainties. So really, yeah, we're working on new one, of course, but saying that, you know, everything is fine in the measurement is also a bit premature, perhaps.
Okay, no, obviously, I mean, if you see this consistent in every channel, this is another story. But until now, the picture we got it in this story is that TTW has a problem only when it's analyzed entering in other analysis. Then this is a different story if you see consistently everywhere.
Yeah,
maybe, sorry. So no, I was wondering that maybe it would be useful to have a clear identification of what kind of phase space these different measurements cover for ttbar W, right? Well, when if you measure ttbar W, what is the selection that you do, and so on, to see, for example, the number of extra jet that you include, automatically or not. So it would be very useful to have exactly the information compare with the selection that you get in a different determination of TTW by itself, or when it's a background to ttbar, when it's a background to 4-tops and so on. Hello, have you heard me? Okay.
Yeah, so Tomasz and Maria are leading the discussion. I'm projecting the slides. And so the question is whether we stay on this slide, move to the other slide, just let us know or come up with any question. This should really be an informal discussion.
So someone was about to speak before. I don't know if it was connected to any of this or any other topic in this page. Okay, so maybe then just we can quickly go through this before moving to the next one. Just a couple more minutes. So there was also the question about finding a way preferred by the theory to be able to suppress ISR effects in order to enhance FSR and vice versa. Trying to identify a region of the phase space in which one or the other can be dominant, just to have a better understanding. Is there any ideas or suggestions there?
So to some extent, the impact of the interference between the initial state and final state in the top pair production was studied in this calculation that we did for top pair production, including the decay in a fully leptonic channel, where the interference, the gluon exchange between the initial state and the final state is fully included. But I mean, we haven't found that the effects of this interference were particularly worrying or large. So maybe I'm not sure. Perhaps someone has experience with other processes. Maybe this is something that someone doesn't have to worry about too much. I mean, if we would consider a different decay channel for the top pair, because this we only did for the leptonic decay.
Mm.
Sorry, and maybe it's a naive question, but when you say final state radiation, you mean from the top, from the decay products of the top, from both? So just to understand.
From the, well, in principle, from all, no? But maybe from the top production.
Okay, just to know this.
Okay, so maybe it's something to check.
Maria, sorry, can you explain what the idea behind this question? So what would you like to study or understand or measure exactly? What is the idea?
So probably being able to identify, so probably in the sense of better assessing systematic uncertainties for our measurements, be able to find a way of having a better way of disentangling one or the other. It's a pity that the person who made this this question could not connect at last minute. So maybe this is something that we can pick up for further discussion later.
Yes, indeed. So I guess we can go to other questions.
So we wanted also to find out about the status of the NLO calculation, including the off-shell effects for the TTTW interference. I don't know if anyone has any updates on this.
I think that in the generator that Thomas mentioned, this TTTW interference for, at least for the polyleptonic channel, is already included in the 4-flavor scheme. And I guess there are works in progress also for other channels, I think.
Okay, that is very good to know.
But that was the status since 2 years, right? The only problem, we still cannot generate properly events, at least in Atlas. But we are putting still efforts. We don't lose hope.
Sorry, my Zoom crashed and I just connected back, and I heard was Lisa talking about BB4 and the production of sample in Atlas. Is it correct?
Yes.
That's correct, yes.
Okay. I mean, do you know at this stage what seems to be the problem, or?
I don't know what's the problem now. I know there were purely technical problems with incompatibilities of some libraries, something like that. So stupid, no, nothing to do with, you know, high-level theory.
Okay.
But unfortunately, that's what we face often, you know.
My understanding is that we're having similar problems in CMS in producing this sample. So it's there is some problem.
Yeah, I believe the latest decision is to have Lizouche files from the authors and then just shower
them out
in Atlas, which is, of course, you know, poor man's solution, but it's still a good thing to have those samples available.
Okay, but sorry, let me intervene at this point. Last time I was discussing with people from Atlas, they had the sample that I comparing as my sample, and there were no differences. So I don't quite understand at this point.
Well, at least it's not yet available for the analysis.
Exactly,
That's
it
for
might
sure.
be a private sample.
Yes.
Yeah, we are not able to produce such a sample in the official production, or yeah.
Again, private sample is fine for initial studies, but you know, it's not practical to go every time to the authors. Authors have something else to do, right? That's why we would like to produce ourselves and be able to, say, change parameters, because we need to define systematics, things like that. So that's why it's not that we're nasty, we just want to make less work for the authors.
Well, yes, of course, but at this point there are no outstanding complaints about this. So I think perhaps we should just rediscuss offline.
Yeah, it seems like that is something you need to figure out. All right, moving on. I would actually like to probably invert these two questions and start better from suggestions for additional observables that we can be measuring, because you've seen in the presentations today of the many different differential measurements that we are performing both in ttbar and single top at the moment. Is there any interesting variable, additional variable, or combination of them that we could use or we could measure to study, for example, additional radiation in pair production? Or additional, any specific variable that we could add to our collection of single top differential measurements? Or even if not only in the resolved case, but also in the boosted, are there any suggestions of measurements that we could add to our portfolio?
So what I can mention, rather than like a variable, but I don't know, this maybe you already explored it. We suggested it in a paper about single top. This was not a fully fledged study, including background, so the situation could be different. But looking at on the rapidity of the light jet when you look in the T-channel signatures, what we noticed is that this is flatter rather than compared to the other background that are entering, like V+jets or contribution from S-channel or TW. And so excluding the central region for the jet may lead to enhance. I'm not saying that this will give you extraordinary results, but it's something that could be at least taken into consideration. I can send you in the chat the link to the paper, and you can look at it. I already presented it in some, for example, CMS top meeting, and this is in a study in a context of electronic correction to single top production. But I can send you the link in the chat.
Yeah, it would be good so that everybody can also
I
have
think it's
it.
more useful to look at that than me explaining without a plot in this thing. No.
Actually, if I may, I would like to revert this question in the following way. So we measure enormous amounts of two-dimensional, now three-dimensional differential distributions. And I personally don't see how this all information can be used for improving the modeling, because there is no one single setup that is good everywhere or is bad everywhere. So how can we use this information?
Yeah, this is a very important point. Thanks, Lisa, for bringing it up. Are there any ideas?
Can you make an explicit example of two-dimensional distributions where the modeling fails for some region? And can you make a few examples, Lisa?
Few examples. Well, I may be not very precise, but normally it's, for example, distribution. For example, ttbar is a function of n-jets, or other parameters as a function of n-jets. So that there are several regions. In some regions, it's perfectly fine, and other regions, it starts to diverge. So a one-dimensional distribution is more straightforward to interpret. While two-dimensional, it seems the differences may be due to perhaps likely due to correlations, and that's not clear how to improve it, or if it's possible to improve it. But there are many cases like that.
Mm-hmm.
I think actually if you go through any of the Atlas or CMS papers on differential measurements, you will see examples for many of these distributions in different, not only in different jet multiplicities, but 2D.
Exactly. I would say majority of 2D are bad in some regions.
Yes.
Oh, yeah, I wanted to know if there is a general feature, or there was some kind of lesson in general. Like, plotting mean, talking like invariant mass and jet multiplicity is, I mean, these are two very different observables, right?
Right, but also it doesn't necessarily, it's not only subject to these. Any 2D measurements, top observables as a function of top observables, or ttbar as a function of top, you can have this, you can see this level of discrepancies.
Exactly. And if you theorists don't look at it, why do we measure it? Sorry, since it's informal discussion. Because it takes enormous efforts to do that. But if it's useless, maybe we shouldn't do that.
Or maybe you have a suggestion of how to narrow it down, because at the moment, so
Exactly.
I recall, so one of the latest CMS papers on differential cross sections was measuring order of 98 distributions. So
right, the one published quite recently in Atlas. It was
right.
like phone book paper. You
Exactly.
tell me distribution, you find it's there. And we justify those publications saying we will use it for improving the modeling, the ttbar modeling.
Maybe even if we are looking at those distributions, maybe we're missing out on some other very particular one that could, for example, allow us to, I don't know, understand better the ttbar production threshold, or can allow us to understand better the different effects going on the threshold or something. And we are just misguided, or we're just measuring something that is actually not that useful, while you could have other ideas that we haven't yet measured that we could be looking at.
Yeah, just an experimentalist comment. This is Yuri. So I guess theorists are not the only customers or partners in the interplay, but also other searchers using ttbar as background or as some tool. So should we also go around our experimental colleagues to see where they see non-description in other search VSM SUSY groups and see what measurements could actually help them? Maybe this is happening. I definitely do not have a broad overview, but experimentalists themselves are customers of ttbar measurements too.
Well, I would say in all remote phase spaces used in searches, they use ttbar control samples to improve ttbar modeling. So the answer is it disagrees everywhere,
yeah.
You know, except for the core, where we tune it to data, at least point plus p phase.
Well, one basic problematic distribution that probably affects many others is the infamous top PT. But this is just...
Oh yeah, but that's one dimension. I mean, that was just one dimensional, right?
Sorry, say again, I couldn't hear properly.
Sorry, it's not a two-dimensional plot. I mean, it's a usual one-dimensional PT of the top indeed. Yeah.
Right, but in the latest measurement, it seems top PT is not the worst one. Of course, there is a slope, but there are many others which are much worse than top PT.
MTT-bar, for example, is not so greatly described. And then, of course, and then if you go constructing 2D differential distributions using these observables, then of course you have discrepancies.
Sorry, but MTT-bar is not great described over the full range or at the threshold?
At the threshold and then in the tail.
Okay.
Oh, and that's not necessarily bad, right? Maybe there is something there.
Right, but we would.
It's funny that we have all this. Oh, maybe there is something that doesn't work. Oh.
That would be great, but we need to rule it out as much as possible.
No, I mean, this also brings me back to one point that we started discussing about the fact, maybe it's more related to data theory comparisons, but to the fact that somewhat in the interpretation that we do lately, somewhat we are obliged to use one distribution at a time because somewhat we don't know the correlations between the various distributions that are published. So I don't know if this is so fits this discussion or not. But sometimes we talk about new observables, but also having I mean 2D distributions, obviously, but also cross correlations between the one-dimensional one or would be very important for us.
But this is something that we are providing from the experiment side, all the correlations between the... we're starting to provide.
Okay, because I mean there are correlations between these in a plot, but not like, you know, if I have a plot of ttbar and the plot of the PT of the top, I don't know the correlation between each plot.
Sure, that's why this is that's true. That's why we are measuring double differentially, and then this is precisely in the direction that we're going. And as Lisa mentioned, also triple differential. We have already done this, and we're going in this direction, and to provide all the necessary correlations between the variables.
Yes, in HEP data.
Yes.
Yeah, perfect. Yeah.
Okay, so if no one wants to bring up anything, then we had another question or comment about how to best do our data to theory comparisons, and this also, or in particular, refers to defining the phase space in which you perform your measurement and to which you correct afterwards. So if there is, there are many discussions at the moment or we are reviving the discussions on what is best to provide the measurements at parton or particle level, in particular when we have additional radiation. And the best way or if it would make sense, or if it would be more valuable to measure the jets at parton level instead of particle level. I don't know if anyone has any thoughts on this. I guess it very much depends on what you want to do with the measurement, to what you want to compare it to. Because if you want to compare it to Monte Carlo simulations, in principle, with the Monte Carlo, you can define your phase space, basically applying very similar cuts. So you can do anything. With how you cluster the jets and everything. But if you want to compare your measurement to fixed order calculations, this of course introduces a big difference in the way you, how you are able to define a jet in the calculation as opposed to what you do in the measurement or in the Monte Carlo. So maybe it's also a little bit the question on what is preferred to do there. What is more useful? Or if both approaches would be the best way to go. For example, does it make sense? Is it useful to measure parton jets differentially?
I think this question is triggered by information we had that clustering into parton jets is closer to what is used in the theory calculation, right, Maria?
Yes, exactly.
Although it's also in our case will be generator dependent. There is no way we can overcome this.
Right.
So you're talking about extra radiation now, only,
yes.
not the tops.
No, not the tops, the additional jets, or even the V+jets that that come from the top. It can also apply in that case.
Yeah, I guess it depends what is your comparison for, right? I mean, if you're typically if you're looking for new physics and so on, then of course you want the information directly from the top. I mean, you want pseudo top or particle tops to be reconstructed, so what and give that information plus jets, and that point is not that critical, I'm saying. Instead, if you're talking about checking the modeling in the spirit that we were discussing before, and then probably depends if you're talking about comparing with a fixed order computation with respect to a Monte Carlo one, right? That also can make a difference. I mean, and then the law is not Monte Carlo, right?
Right.
So there, if you want to compare with that tool or prediction, then you probably maybe you want to go closer to what their definition of a jet is. That's also a possibility. However, one has to know that again, for you to go back to something means that you're folding in Monte Carlo information, right? Somewhat.
Yes.
Or deconstructing, if you want, something from the Monte Carlo. So you feed in the Monte Carlo dependencies in the end. So it's very hard to decide exactly where the optimal choice is, I guess, in general.
Yeah, probably the easy answer is do both.
Yeah, probably.
But of course, this is
usual. As usual, the answer is do everything.
Exactly, but
we are slowly reaching the time allocated for the discussion. Of course, I don't want to interrupt if anyone would like to discuss further, but perhaps it's time to ask for last questions, quick questions and remarks about anything that was discussed during today's sessions, or about anything we discussed in this discussion.
we have more tomorrow, so
yes, of course. There's going to be more discussions on top-quark
tomorrow
properties.
will be on properties and EFT, but of course we can bring up anything. Or theorists, do you have questions for us?
Or requests.
Or requests.
I think what Fabio already said before about the TTW, that it's interesting to know exactly what has been measured for TTW in the different cases, the phase spaces, to really understand if what is important, I think, to me is to understand if it's something related to the hard process itself of the really for the final state signature selection. So if it's something that has to be improved in the direction of NN and OQCD, or it's something that has to be improved in the simulation of other effects that happen after the decay of the tops and extra radiation. This is crucial to understand what's going on there. Because maybe also there could be new physics, not only in the MTT distribution.
Sure.
But, we have to be sure. And until now, we said it's not new physics, but yeah, we have to rule it out. Yeah.
Sure, this is a good point that we can follow up on. Yes.
The other, maybe the other question, which would be nice to have even a list of maybe of the observables or two-dimensional distributions where, say, the discrepancies with the modeling are the most glaring. Or so, I mean, it's good to have 100 distributions, but it's also somewhat difficult then to look at them with the eyes, so to see whether there are, if there is a story behind, right? If there are structures coming out. And the other thing is, of course, whether there are, these kind of problems are both in CMS and Atlas, or if you want, if they are both in semi-lepton, one lepton final state and fully hadronic, or two lepton final state. I mean, to see whether there are also regularities, because otherwise, with so much information, it's easy, I guess, to get lost and maybe to miss the main structures and aspects.
Yeah. Yes, that is true. And the only thing is that we are only starting now to produce both Atlas and CMS, these 2D differential cross sections, and we're not always measuring the same in the same observables to be able to make a comparison like what you're asking, to understand if the discrepancies that we observe are in the same phase spaces, in the same pairs of observables and things like this. So this of course will we will need a bit. We're only starting to make these kind of comparisons, if at all, only now.
But maybe we still can select some subsets,
Sure.
overlapping, yeah.
Sure.
To start.
I mean, even for tomorrow, I mean, if we had at least, even for tomorrow in discussion, people doing EFT are very interested in whether to know, for example, if there is some deviation in the tail of MTT, which is everywhere, right? For example, in all final states and both in Atlas and CMS, then you would certainly get the attention of many theorists.
Mm-hmm.
Not only people expert in Monte Carlo, I mean, or in precision predictions, but even modern builders and so on. So it's really important, I guess, to have something where at least we can start discussing maybe a few examples, glaring.
No, absolutely. I mean, we can try to put something, collect something for tomorrow. If not, we can, of course, have a dedicated meeting. One very good scenario for these kind of discussions is the LHC working group that I advertise here, not because I am the contact for CMS, but
yeah, but also top 2020 is coming.
And top
still,
2020.
right?
It's
Soon,
earlier than
so
that.
yes.
Well, that would be a very nice venue for.
That's right.
We are scheduling something about this, I think, or at least there was some intention. Anyway, yeah, absolutely, sure.
That's
and
excellent.
These discussions, they are potentially very interesting because they put together all different people, right? People who do this precision.
Yes.
And also people who are interested in new physics, for example. So.
Yes.
Yeah.
Exactly. Okay, so maybe we should be wrapping up.
Yes, thank you. Thank you very much all for joining us tonight. Special thanks goes to people who connected externally to provide extra expertise. And don't forget, tomorrow there's going to be a discussion on top quark properties and EFT interpretations. So so do please tune in tomorrow as well. And I guess we'll all see each other at tomorrow's sessions.
Yes, very good.
Yeah, thanks, Maria. Thanks, Thomas. Thanks, everybody, and hear you and see you tomorrow. Bye-bye.
Bye-bye.
Bye. Bye. Thanks.
Bye.